code. So when in doubt, run the provided code and experiment. Your teacher for this course is Daniel Bork. Daniel is a machine learning engineer and popular course creator. So enjoy the course and don't watch the whole thing in one sitting.
Hello, welcome to the video. It's quite a big one. But if you've come here to learn machine...
Alright, just testing my mic here. Hello, testing my mic here. Alright, that works good. Oh, did we have a second viewer? I think we had one. Let's remove this mess. Alright. Let me just adjust this. Right. So I had to cut my morning stream short. Yeah, so I'm gonna do a continuation stream, if you want to put it that way, as I'm just gonna continue from where I left off. And yeah, excited to learn as always, and let's see the progress that I make. So I'll be streaming continuously for 2 hours, then take a break for 20 minutes at the 2-hour mark. So that's the plan. Hopefully power doesn't go down, or things which can't be avoided, things like that doesn't come up. Alright, with that being said, let's get started. I think I need to set up Google Colab again, don't I? Titled one. I could swear we had a second viewer though, I don't know who it was.
important machine learning concepts by writing Pytorch code. Now, if you get stuck, you can leave a comment below.
Alright, let's go to the part we were at before the stream ended, which was...
Still looking for the best smartphone under 15K? Check out the Infinix Note 40X 5G.
It was on Pytorch training loop.
Welcome back. In the last video, we set up a loss function and we set up an optimizer and we discussed the roles of each. So the loss function measures how wrong our model is. The optimizer talks to the loss function and goes, well, if I change these parameters a certain way, does that reduce the loss function at all? And if it does, yes, let's keep adjusting them in that direction. If it doesn't, let's adjust them in the opposite direction. And I just want to show you, I added a little bit of text here just to concretely put down what we were discussing. Inside the optimizer, you'll often have to set two parameters, params and LR, where params is the model parameters you'd like to optimize. For an example, in our case, params equals our model 0 parameters, which were, of course, a weight and a bias, and the learning rate, which is LR in optimizer. LR stands for learning rate, and the learning rate is a hyperparameter. Our whole goal is to reduce the MA. We'll talk it all through. I want to look at it to the output layer. So starting here, input layer. So we'll go back down here to calculate prediction labels. Put too much there. Ooh, loss on models. Essentially, how do I learn shit down here? So is a gradient. Change an X gradient over here. Bottom. You start bottom of the gradient. Always loop and race it. Machine right. Touch training. Smoke. I did that parameter. But parameter. I suppose that require gradient thing with the grid is take off loop in the next video. I'll see you there. Friends, welcome back. In the last video, I promised a lot of code, but we didn't get there. We discussed some important steps. I forgot how much behind the scenes there is to a Pytorch training loop. And I think it's important to spend the time to analyze it. We're going to see that later on in the course, and it's going to run behind the scenes for us. But we're spending a fair bit of time here because this is literally the crux of how our model learns. So let's get into it. So now we're going to implement the forward pass, which involves our model's forward function, which we defined up here when we built our model. The forward pass runs through this code here. So let's just write that. So in our case, because we're training, I'm just going to write here. This is training. We're going to see .eval later on. We'll talk about that when it comes. Let's do the forward pass. So the forward pass, we want to pass data through our model's forward method. We can do this quite simply by going ypred, so y predictions, because remember, we're trying to use, our ideal model is using x test to predict y test on our test data set. We make predictions on our test data set, we learn on our training data set. So we're passing, I'm just going to get rid of that because we don't need that. So we're passing our model xtrain, and model 0 is going to be our current model. There we go. So we learn patterns on the training data to evaluate our model on the test data. Number 2, where are we at? So we have to calculate the loss. Now, in a previous video, we set up a loss function. So this is going to help us calculate the what. What kind of loss are we using? We want to calculate the MAE. So the difference or the distance between our red dot and a green dot. And the formula would be the same if we had 10,000 red dots and 10,000 green dots. We're calculating how far they are apart, and then we're taking the mean of that value. So let's go back here. So calculate the loss. And in our case, we're going to set loss equal to our loss function, which is L1 loss in Pytorch, but it is MAE, ypred, and ytrain. So we're calculating the difference between our model's predictions on the training data set and the ideal training values. And if you want to go into torch.nn loss functions, that's going to show you the order, because sometimes this confuses me too, what order the values go in here, but it goes prediction first, then labels. I may be wrong there, because I get confused here. My dyslexia kicks in, but I'm pretty sure it's predictions first, then actual labels. Do we have an example of where it's used? Yeah, input first, target next. So there we go. And truth be told, because it's mean absolute error, it shouldn't actually matter too much. But in the case of staying true to the documentation, let's do inputs first and then targets next for the rest of the course. Then we're going to go optimizer 0 grad. Haven't discussed this one, but that's okay. I'm going to write the code and then I'm going to discuss what it does. So what does this do? Actually, before we discuss this, I'm going to write these two steps because they kind of all work together. And it's a lot easier to discuss what optimizer 0 grad does in the context of having everything else. Perform back propagation on the loss with respect to the parameters of the model. Back propagation is going to take the loss value, so loss backward. I always say backwards, but it's just backward. That's the code there. And then number 5 is step the optimizer. So perform gradient descent. So optimizer.step. Look at us. We just wrote the 5 major steps of a training loop. Now let's discuss how all of these work together. So it's kind of strange, like the ordering of these. You might think, oh, what should I do the order? Typically the forward pass and the loss come straight up. Then there's a little bit of ambiguity around what order these have to come in, but the optimizer step should come after the back propagation. So I just like to keep this order how it is because this works. Let's just keep it that way. But what happens here? Well, it also is a little bit confusing in the first iteration of the loop because we've got 0 grad. But what happens here is that the optimizer makes some calculations in how it should adjust model parameters with regards to the back propagation of the loss. And so by default, these will...
Wait a second. Okay, so first we do the loss, okay, and then what is 0 grad?
0 grad. Haven't discussed this one, but that's okay. I'm going to write the code and then I'm going to discuss what it does. So what does this do? Actually, before we discuss this, I'm going to write these two steps because they kind of all work together. And it's a lot easier to discuss what optimizer 0 grad does in the context of having everything else.
All right.
Perform back propagation on the loss with respect to the parameters of the model. Back propagation is going to take the loss value, so loss backward. I always say backwards, but it's just backward. That's the code there. And then number 5 is step the optimizer. So perform gradient descent. So optimizer.step. Look at us. We just wrote the 5 major steps of a training loop. Now let's discuss how all of these work together. So it's kind of strange, like the ordering of these. You might think, oh, what should I do the order? Typically the forward pass and the loss come straight up. Then there's a little bit of ambiguity around what order these have to come in, but the optimizer step should come after the back propagation. So I just like to keep this order how it is because this works. You might think, oh, what should I do the order? Typically the forward pass and the loss come straight up. Then there's a little bit of ambiguity around what order these have to come in, but the optimizer step should come after the back propagation. So
the optimizer step should come up after the backward propagation. Then what is 0 grad?
So I just like to keep this order how it is because this works. Let's just keep it that way. But what happens here? Well, it also is a little bit confusing in the first iteration of the loop because we've got 0 grad. But what happens here is that the optimizer makes some calculations in how it should adjust model parameters with regards to the back propagation of the loss. And so by default, these will, by default, how the optimizer changes will accumulate through the loop. So we have to 0 them above in step 3 for the next iteration of the loop. So a big long comment there, but what this is saying is above in step 3 for the next iteration of the loop. So a big long comment there, but what this is saying is, let's say we go through the loop and optimizer chooses a value of 1, change it by 1, and then it goes through a loop again. If we didn't zero it, if we didn't take it to 0 because that's what it's doing, it's going 1 to 0, it would go, okay, next 1, 2, 3, 4, 5, 6, 7, 8, all through the loop, right? Because we're looping here. If this was 10, it would accumulate the value that it's supposed to change 10 times. But we want to start again, start fresh each iteration of the loop. And now the reason why it would accumulate the value that it's supposed to change 10 times. But we want to start again, start fresh, right? Well, comment there, but what this is saying is, let's say we go through the loop and optimizer chooses a value of 1, change it by 1, and then it goes through a loop again. If we didn't zero it, if we didn't take it to 0 because that's what it's doing, it's going 1 to 0, it would go, okay, next 1, 2, 3, 4, 5, 6, 7, 8, all through the loop, right? Because we're looping here. If this was 10, it would accumulate the value that it's supposed to change 10 times. But we want to start again, start fresh each iteration of the loop. And now the reason why it accumulates, that's pretty deep in the Pytorch documentation. From my understanding, there's something to do with like efficiency of computing. If you find out what the exact reason is, I'd love to know. So we have to 0 it, then we perform back propagation. If you recall, back propagation is find out ratio with what of them.
But let me lower the playback speed and listen to it more
above
carefully.
In step 3 for the next iteration of the loop. So a big long comment there, but what this is saying is, let's say we go through the loop and the optimizer chooses a value of 1, change it by 1, and then it goes through a loop again. If we didn't zero it, if we didn't take it to 0 because that's what it is doing, it's going 1 to 0, it would go, okay, next 1, 2, 3, 4, 5, 6, 7, 8, all through the loop, right? Because we're looping here. If this was 10, it would accumulate the value that it's supposed to change 10 times. But we want it to start again,
Oh, so the first time if it does, because we've said the, is it trying to say that first time it has the learning rate of 0.01, next time if we do not have this method, if you do not call dot step, what would happen is the next time the change would be 0.02, then 0.03, and so on. At least that's what I understood from that. Let's do some digging ourselves. What does optimizer step 2? Pytorch. Let's see. Yep. Gradients are stored by tensors themselves. Okay. Once you call backward on the loss, after computing the gradients for all tensors in the model, calling optimizer.step makes the optimizer iterate over all parameters it is supposed to update and use the internally stored grad to update the values. Didn't quite get that. Maybe let's go here. Optimizer step. Yeah, maybe let's go into this. Can someone explain what's the difference between step, backward, and what they do? Alright. And so can you explain when you should? Hopefully you can use in the zero grad clears all gradients. I was gonna pronounce ingredients. Okay. Zero grad clears all gradients from the last step. Otherwise, you'll just accumulate gradients from all lost or backward calls. Oh, I see. Because the tensor stores the gradients. If you call zero grad, it just has the newest gradient in it, because we don't need the old gradients, so it becomes faster. Then what does optimizer.step do then? Loss.backward computes the this uses back propagation and does the all algorithm for that. Optimizer.step causes the optimizer to take a step based on the gradients of the parameters. Okay, based on the loss function, it adjusts itself. Oh, okay. So since the tensors store the gradients, if we don't have zero grad, what happens is that the gradients will just be stored again and again and again, which would increase our computation time. So that's why we have that.
Fresh each iteration of the loop. And now the reason why it accumulates, that's pretty deep in the Pytorch documentation. From my understanding, there's something to do with like efficiency of compute. Now the reason why it accumulates, that's optimization of the loop. So a big long comment there, but what this is saying is, let's say we go through the loop and the optimizer chooses a value of 1, change it by 1, and then it goes through a loop again. If we didn't zero it, if we didn't take it to 0, because that's what it is doing, it's going 1 to 0, it would go, okay, next 1, 2, 3, 4, 5, 6, 7, 8, all through the loop, right? Because we're looping here. If this was 10, it would accumulate the value that it's supposed to change 10 times. But we want it to start fresh each iteration of the loop. And now the reason why it accumulates, that's pretty deep in the Pytorch documentation. From my understanding, there's something to do with like efficiency of computing. If you find out what the exact reason is, I'd love to know. So we have to zero it, then we perform backpropagation. If you recall, backpropagation is discussed in here. And then with optimizer step, we form gradient descent. So the beauty of Pytorch, this is the beauty of Pytorch, is that it will perform backpropagation, we're going to have a look at this in a second, and gradient descent for us. So to prevent this video from getting too long, I know we've just written code, but I would like you to practice writing a training loop yourself. Just write this code and then run it and see what happens. Actually, you can comment this out. We're going to write the testing loop in a second. So your extracurriculum for this video is to, 1, rewrite this training loop, is to, 2, sing the Pytorch optimization loop song. Let's go into here.
All right. You know what, let's actually do that before we move forwards. So I'm just gonna do a new code block and just hide that so I don't see what's going on. So I need a new training block. For that I'm gonna set our number of iterations or epochs as it is called here to, I set it to 20 since we're not gonna run this one anyways. Oh, you know what, let's just set it to 10. It was 10 in the earlier one. Anyhow, what we're gonna do now is we're gonna do a for loop for epoch and epochs. I mean range of epochs. Remember, epochs is a number. Alright, now what we're gonna do is we're gonna make our predictions first. So we're gonna call dot train. We're gonna train the model first, then we are gonna get our predictions. That would be for model 0 with the X train. Okay, so we have got our predictions. Now we are gonna calculate our loss. So loss is gonna be, actually I need to take a look at the code back again. I already forgot what it is. Okay, and then we by getting the predictions, I meant do the forward pass, whatever function we had assigned it. Then we calculate the loss. No, we're on track actually. Oops, what did I do here? Loss optimize. Okay, so we're going to call the loss function. We're going to keep true to our documentation. We're going to pass it the what it predicted and our X train in it, right? So we need to do, oh no, not our X train. Oh no, because X train and Y train are the exact values. So if it needs to calculate the loss, we need to give it the predictions made alongside with the actual result, which is Y train. Yep. So we have our loss now, and next what we need to do is so we have our loss, and we are gonna do back propagation. Is it loss dot backward or? Yep. Right, that's what we're gonna do, and then we're gonna optimize it to the next step. We're gonna optimize the function based on our loss. Now we're gonna place this here, which is optimizer dot 0 grad. This is needed so that we don't accumulate our gradients again and again and again. So that should be good. And terms of gradient tracking, well, we'll get there. Let's just create our model again. Let's run this. Yeah, we need what? We'll have to run all of this up. Runtime, run all. Okay, cool. So
if you want to remember the steps, well, I've got a song for you. This is the training loop song. We haven't discussed the test step, but maybe you could try this yourself. So, and this is an old version of the song, actually. I've got a new one for you. But let's sing this together. It's train time. So we do the forward pass, calculate the loss, optimize a 0 grad, loss backwards, optimize a step, step, step. Now, you only have to call optimize a step once. This is just for jingle purposes. But for test time, let's test. Pytorch no grad, do the forward pass, calculate the loss, watch it go down, down, down. And that's from my Twitter. But this is a way that I help myself remember the steps that are going on in the code here. And if you want the video version of it, well, you're just going to have to search unofficial Pytorch optimization loop song. Oh, look at that. Who's that guy? Well, he looks pretty cool.
Wait, let's see. Unofficial. Pytorch optimization loop song.
And we're back. The team is looking down the barrel of a 4:55 meeting.
Oh, excuse me. How convenient and on microphone. And apologies for the train wreck of a room. If I'd known I'd have visitors, I probably would have cleaned up a little. But you see, I'm coding some Pytorch over here, specifically learning about Pytorch optimization loops, like a Pytorch training loop and a Pytorch testing loop or an eval loop. And you know what? There's a fair few steps in there to remember. So I wrote a little jingle to help me remember, and you possibly remember too. And that way we can never forget. So let's train. For an epoch in a range, Comauto.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Comauto.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Let's do it again, again, again. For another epoch, Comauto.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Comauto.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Let's do it again, again, again. For another epoch, Comauto.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Let's test. Comauto.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Keep going if you want, but don't forget to save, save, save. But of course, due to the Pythonic nature of Pytorch, you don't necessarily have to learn that jingle off by heart. As fun as it is, you can functionize the training loop and the test loop, so you can save them and call them again, again, again.
Look at this guy. This is like, he's doing quite a lot.
So I'll let you check that out in your own time. But for now, go back through the training loop steps. I've got a colourful graphic coming up. In the next video, we're going to write the testing steps. And then we're going to go back one more time and talk about what's happening in each of them. And again, if you'd like some even more extra curriculum, don't forget the videos I've shown you on backpropagation and gradient descent. But for now, let's leave this video here. I'll see you in the next one. Friends, welcome back. In the last few videos, we've been discussing the steps in a training loop in Pytorch, and there's a fair bit going on. So in this video, we're going to step back through what we've done just to recap, and then we're going to get into testing. And it's nice and early where I am right now. The sun's about to come up. It's a very, very beautiful morning to be writing code. So let's jump in. We've got a little song here for what we're doing in the training steps. For an epoch in a range, Comauto.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. That's the little jingle I use to remember
Oh my god, I learned this song already.
the steps in here, because the first time you write it, there's a fair bit going on. But subsequent steps and subsequent times that you do write it, you'll start to memorize this, and even better, later on, we're going to put it into a function so that we can just call it over and over and over and over again. With that being said, let's jump in to a colorful slide, because that's a lot of code on the page. Let's add some color to it, understand what's happening. That way you can refer to this and go, I see what's going on now. So for the loop, this is why it's called a training loop. We step through a number of epochs. One epoch is a single forward pass through the data. So pass the data through the model for a number of epochs. Epochs is a hyperparameter, which means you could set it to 100, you could set it to 1,000, you could set it to 1, as we're going to see later on in this video. We skip this step with the colors, but we put the model in, we call model.train. This is the default mode that the model is in. Essentially, it sets up a whole bunch of settings behind the scenes in our model parameters so that they can track the gradients and do a whole bunch of learning behind the scenes with these functions down here. Pytorch does a lot of this for us. So the next step is the forward pass. We perform a forward pass on the training data in the training loop. This is an important note. In the training loop is where the model learns patterns on the training data. Whereas in the testing loop, we haven't got to that yet, is where we evaluate the patterns that our model has learned, or the parameters that our model has learned on unseen data. So we pass the data through the model. This will perform the forward method located with that our model has learned. In the testing loop, we haven't got to that yet, training loop is where the model learns patterns on the training data. Whereas in the testing loop, we haven't got to that yet, is where we evaluate the patterns that our model has learned, or the parameters that our model has learned on unseen data. So we pass the data through the model. This will perform the forward method located within the model object. So because we created a model object, you can actually call your models whatever you want, but it's good practice to, you'll often see it just called model. And if you remember, we'll go back to the code. We created a forward method in our model up here, which is this. Because our linear regression model class subclasses nn.module, we need to create our own custom forward method. So that's why it's called a forward pass, is because not only does it, well, the technical term is forward propagation. So if we have a look at a neural network picture, forward propagation just means going through the network from the input to the output. There's a thing called back propagation, which we're going to discuss in a second, which happens when we call loss.backward, which is going backward through the model. But let's return to our colorful slide. We've done the forward pass, call a forward method, which performs some calculation on the data we pass it. Next is we calculate the loss value, how wrong the model's predictions are. And this will depend on what loss function you use, what kind of predictions your model is outputting, and what kind of true values you have. But that's what we're doing. Here, we're comparing our model's predictions on the training data to what they should ideally be. And these will be the training labels. The next step, we zero the optimizer gradients. So why do we do this? Well, it's a little confusing for the first epoch in the loop, but as we get down to optimizer.step here, the gradients that the optimizer calculates accumulate over time, so that for each epoch, for each loop step, we want them to go back to 0. And now the exact reason behind why the optimizer accumulates gradients is buried somewhere within the Pytorch documentation. I'm not sure of the exact reason. From memory, it's because of compute optimization. It just adds them up in case you wanted to know what they were. But if you find out exactly, I'd love to know. Next step is to perform back propagation on the loss function. That's what we're calling loss.backward. Now, back propagation is we compute the gradient of every parameter with requires grad equals true. And if you recall, we go back to our code. We've set requires grad equals true for our parameters. Now, the reason we've set requires grad equals true is not only so back propagation can be performed on it, but let me show you what the gradients look like. So let's go loss function curve. That's a good idea. So we're looking for some sort of convex curve here. There we go, L2 loss. We're using L1 loss at the moment. Is there a better one here? All we need is just a nice looking curve. Here we go. So this is why we keep track of the gradients. Behind the scenes, Pytorch is going to create some sort of curve for all of our parameters that looks like this. Now, this is just a 2D plot. So the reason why we're just using an example from Google Images is, one, because you're going to spend a lot of your time Googling different things. And two, in practice, when you have your own custom neural networks, right now we only have 2 parameters. So it's quite easy to visualize a loss function curve like this. But when you have, say, 10 million parameters, you basically can't visualize what's going on. And so Pytorch, again, will take care of these things behind the scenes. But what it's doing is when we say requires grad, Pytorch is going to track the gradients of each of our parameters. And so what we're trying to do here with backpropagation and subsequently gradient descent is calculate where the lowest point is. Because this is a loss function, this is MSE loss, we could trade this out to be MAE loss in our case, or L1 loss for our specific problem. But this is some sort of parameter, and we calculate the gradients because what is the gradient? Let's have a look. What is a gradient? A gradient is an inclined part of a road or railway. No, we want it in machine learning. What's it going to give us? In machine learning, a gradient is a derivative of a function that has more than one input variable. Okay, let's dive in a little deeper. See, here's some beautiful loss landscapes. We're trying to get to the bottom of here. This is what gradient descent is all about. So, oh, there we go. So this is a cost function, which is also a loss function. We start with a random initial variable. What have we done? We've started with a random initial variable, right? Okay, and then we take a learning step. Beautiful. This is W, so this could be our weight parameter. Okay, we're connecting the dots here. This is exciting. We've got a lot of tabs here, but that's all right. We'll bring this all together in a second. And what we're trying to do is come to the minimum. Now, why do we need to calculate the gradients? Well, the gradient is what? Oh, value of weight. Here we go. This is even better. I love Google Images. So this is our loss, and this is the value of a weight. So we calculate the gradients. Why? Because the gradient is the slope of a line, or the steepness. And so if we calculate the gradient here, and we find that it's really steep, right at the top of this incline, we might head in the opposite direction to that gradient. That's what gradient descent is. And so if we go down here, now, what are these step points? There's a little thing that I wrote down in the last video, at the end of the last video, I haven't told you about yet, but I was waiting for a moment like this. And if you recall, I said kind of all of these 3 steps, optimizer zero grad, loss backward, optimizer step are all together. So we calculate the gradients because we want to head in the opposite direction of that gradient to get to a gradient value of 0. And if we get to a gradient value of 0 with a loss function, well, then the loss is also 0. So that's why we keep track of it. And if we get to a gradient value of 0 with a loss function, well, then the loss is also 0.
If we had to... Yeah, because if the gradient is 0, that means it's flat. Hence it's at the lowest point. You can't go further lower.
Oh.
Yeah.
So that's why we keep track of the gradient with requires grad equals true. And again, Pytorch does a lot of this behind the scenes. And if you want to dig more into what's going on here, I'm going to show you some extra resources for backpropagation, which is calculating this gradient curve here, and gradient descent, which is finding the bottom of it towards the end of this video. And again, if we started over this side, we would just go in the opposite direction of this. So maybe this is a positive gradient here, and we just go in the opposite direction here. We want to get to the bottom. That is the main point of gradient descent. And so if we come back, I said, just keep this step size in mind here. If we come back to where we created our loss function and optimizer, I put a little tidbit here for the optimizer, because we've written a lot of code and we haven't really discussed what's going on, but I like to do things on the fly as we need them. So inside our optimizer, we'll have main two parameters, which is params. So the model parameters you'd like to optimize, params equals model 0.parameters in our case. And Pytorch is going to create something similar to this curve, not visually, but just mathematically behind the scenes for every parameter. Now, this is a value of weight, so this would just be potentially the weight parameter of our network. But again, if you have 10 million parameters, there's no way you could just create all of these curves yourself. That's the beauty of Pytorch. It's doing this behind the scenes through a mechanism called Torch autograd, which is auto-gradient calculation. And there's beautiful documentation on this. If you'd like to read more on how it works, please go through that. But essentially behind the scenes, it's doing a lot of this for us, for each parameter. That's the optimizer. Then within the optimizer, once we've told it what parameters to optimize, we have the learning rate. So the learning rate is another hyperparameter that defines how big or small the optimizer changes the parameters with each step. So a small learning rate results in small changes, whereas a large learning rate is in large changes. And so if we look at this curve here, we might at the beginning start with large steps, so we can get closer and closer to the bottom. But then as we get closer and closer to the bottom, to prevent stepping over to this side of the curve, we might do smaller and smaller steps. And the optimizer in Pytorch, there are optimizers that do that for us, but there is also another concept called learning rate scheduling, which is, again, something if you would like to look up and do more. But learning rate scheduling essentially says, hey, maybe start with some big steps, and then as we get closer and closer to the bottom, reduce how big the steps are that we take. Because if you've ever seen a coin at back of couch, this is my favorite analogy for this. If you've ever tried to reach a coin at the back of a couch, like this excited young chap, if you're reaching towards the back of the couch, you take quite big steps as you, say your arm was over here, you would take quite big steps until you get to about here. And then the closer you get to the coin, the smaller and smaller your steps are. Otherwise, what's going to happen? The coin's going to be lost. Or if you took 2 small steps, you'd never get to the coin. It would take forever to get there. So that's the concept of the learning rate. If you take 2 big steps, you're going to just end up over here. If you take 2 small steps, it's going to take you forever to get to the bottom here. And this bottom point is called convergence. That's another term you're going to come across. I know I'm throwing a lot of different terms at you, but that's the whole concept of the learning rate. How big is your step down here in gradient descent? Gradient descent is this. Backpropagation is calculating these derivative curves or the gradient curves for each of the parameters in our model. So let's get out of here. We'll go back to our training steps. Where were we? I think we're up to backpropagation. Have we done backward? Yes. So the backpropagation is where we do the backward step. So the forward pass, forward propagation, go from input to output. Backpropagation, we take the gradient of the loss function with respect to each parameter in our model by going backwards. That's what happens when we call loss.backward. Pytorch does that for us behind the scenes. And then finally, step number 5 is step the optimizer. We've kind of discussed that. As I said, if we take a step, let's get our
viewer right now. Well, besides me anyway. Hey there. Thank you for, coming in. Just learning AI stuff right now.
Loss curve back up. Loss function curve. Doesn't really matter what curve we use.
Feel free to ask
the optimizer step is taking a step this way to try and optimize the parameters so that we can get down to the bottom here. And I also just
have a goal to fulfill.
Noted here that you can turn all of this into a function, so we don't necessarily have to remember to write these every single time. The ordering of this, you'll want to do the forward pass first, and then calculate the loss, because you can't calculate the loss unless you do the forward pass. I like this ordering here of these 3 as well, but you also want to do the optimizer step after the loss backward. So this is my favorite ordering. It works. If you like this ordering, you can take that as well. After that, like these here is taking a step this way to try and optimize the parameters so that we can get down to the bottom here. And I also just noted here that you can turn all of this into a function, so we don't necessarily have to remember to write these every single time. The ordering of this, you'll want to do the forward pass first, and then calculate the loss, because you can't calculate the loss unless you do the forward pass. I like this ordering here of these 3 as well, but you also want to do the optimizer step after the loss backward. So this is my favorite ordering. It works. If you like this ordering, you can take that as well. With that being said, I think this video has gotten long enough. In the next video, I'd like to step through this training loop, 1 epoch at a time, so that we can see, I know I've just thrown a lot of words at you, that this optimizer is going to try and optimize our parameters each step, but let's see that in action, how our parameters of our model actually change every time we go through each one of these steps. So I'll see you in the next video. Let's step through our model. Welcome back. Now we've spent a fair bit of time on the training loop and the testing loop. Well, we haven't even got to that yet, but there's a reason behind this, because this is possibly one of the most important things, aside from getting your data ready, which we're going to see later on in Pytorch deep learning, is writing the training loop, because this is literally like how your model learns patterns and data. So that's why we're spending a fair bit of time on here. And we'll get to the testing loop, because that's how you evaluate the patterns that your model has learned from data, which is just as important as learning the patterns themselves. And following on from the last couple of videos, I've just linked some YouTube videos that I would recommend for extra curriculum for backpropagation, which is what happens when we call loss.backward down here. And for the optimizer step, gradient descent is what's happening there. So I've linked some extra resources for what's going on behind the scenes there from a mathematical point of view. Remember, this course focuses on writing Pytorch code, but if you'd like to dive into what math Pytorch is triggering behind the scenes, I'd highly recommend these two videos. And I've also added a note here as to which loss function and optimizer should I use, which is a very valid question. And again, it's another one of those things that's going to be problem specific. But with experience over time, you work with machine learning problems, you write a lot of code, you get an idea of what works and what doesn't with your particular problem set. For example, like a regression problem like ours, regression is again predicting
like everything, experience takes over.
a number. We use MAE loss, which Pytorch causes L1 loss. You could also use MSE loss, and an optimizer like Torch, Optim, stochastic gradient descent will suffice. But for classification, you might want to look into...
I wonder what does I know what an MAE loss is now. Mean average loss. What is an MSE loss? Let's check. C loss, Pytorch. What is MSE loss? Mean squared error loss. Interesting. Is this the kind of the mathematical formula for this? Weighted mean square loss. Oh, you just square. I think this is what it means. You just square the x and y coordinates like they're different and just add them up. We have to see input minus target square. Input minus target square. And then we sum all of them up. Alright, I guess we'll look into the math when we come to use it. For the time being,
binary classification, a binary cost entropy loss, but we'll look at a classification problem later on in the course. For now, I'd like to demonstrate what's going on in the steps here. So let's go model 0. Let's look up the state dict and see what the parameters are for now. Now, they aren't the original ones, I don't think. Let's reinstantiate our model so we get new parameters.
I've already done that.
Yeah, we recreated it here. I might just get rid of that. So we'll rerun our model code, rerun model state dict, and we will create an instance of our model and just make sure your parameters should be something similar to this. If it's not exactly like that, it doesn't matter, but yeah, I'm just going to showcase. You'll see on my screen what's going on.
Wait, what did you do?
Dict, and we will create an instance of our model and just make sure your parameters should be something similar to this. If it's not exactly like that, it doesn't matter, but yeah, I'm just going to showcase. You'll see on my screen what's going on anyway. State dict 3367 for the weight and 01288 for the bias. And again, I can't stress enough, we've only got 2 parameters for our model and we've set them ourselves. Future models that you build and later ones in the course will have much, much more, and we won't actually explicitly set any of them ourselves. We'll check out some predictions. They're going to be terrible because we're using random parameters to begin with, but we'll set up a new loss function and an optimizer. Optimizer is going to optimize our model 0 parameters, the weight and bias. The learning rate is 0.01, which is a relatively large step. That would be a bit smaller. Remember, the larger the learning rate, the bigger the step, the more the optimizer will try to change these parameters every step. But let's stop talking about it. Let's see it in action. I've set a manual seed here too, by the way, because the optimizer's steps are going
to say. Like, we've been just discussing. I won't say we've been discussing theory for too long, but it feels like it's. Let's run the code and see the output.
It'll be quite random as well, depending on how the model's predictions go. But this is just to try and make it as reproducible as possible. So keep this in mind. If you get different values to what we're going to output here from my screen to your screen, don't worry too much. What's more important is the direction they're going. So ideally, we're moving these values here. This is from we did.
Okay, model 0.eval. Did he run it or no? He didn't run it.
One epoch before. We're moving these values closer to the true values, and in practice, you won't necessarily know what the true values are. But that's where evaluation of your model.
You know what? Let's write those 2 code blocks. And you have what the weight and bias needs to be, which we are hiding from the code anyways. Alright, so currently, I guess it ran because I could swear it was different. I think I ran it accidentally. Let's just run these 2 code blocks. Manual seed. Now if I run this, I should get, yeah, there we go. So we ran it and it predicted that the weight is higher and the bias is higher, which is good. So I think if we do it a couple of times, let's test it out. We can always go back and be. So if we do it 100 times, let's see what the value is now. Wait, I didn't change. Maybe I did not run it. Wait, what? Okay, let's just do it one time. Huh? Maybe I might have done something else, I guess. Anyhow, let's just reset it just in case,
Model comes in. We're going to cover that when we write a testing loop. So let's run one epoch. Now I'm going to keep that down there. Watch what happens. We've done one epoch, just a single epoch.
Wait, how did you do it? I did the same thing too, right? Okay, first I need to set the... I did not set the manual seed, maybe... Well, I don't think that should change anything though, but still, let's set it. Yep, there's a typo over there. Nope, no need of that white space.
We've done the forward pass, we've calculated the loss, we've done...
Let that run, and let's do this. Why don't these values change? Maybe I'm not running it correctly. We train it, we predict it, loss, calculate loss, backward step, eval, run it again. And now give me the... You know what, let me just have it in another what, code block. Okay, alright. I guess I had to set this up again. Maybe some issue with Google Colab.
Optimizer 0 grad, we perform back propagation, and we step the optimizer. What does stepping the optimizer do? It updates our model parameters to try and get them further closer towards the weight and bias. If it does that, the loss will be closer to 0. That's what it's trying to do. How about we print out the loss at the same time? Print loss and the loss. Let's take another step. So the loss is 0.
Oh, why did I print the loss, huh? Let's do the same.
.301. Now we check the weights and the bias. We've changed again. 3.
Yeah.
3, 4, 4, 5, 1, 4, 8, 8. We go again. Oh, the loss is going down. Check it.
Yeah, meaning they are getting closer.
Hey, look at that. The values are getting closer to where they should be, if ever so slightly. Loss went down again. Oh my goodness, this is so amazing. Look, we're training our... Let's print this out in the same cell. Print out model state dict. We're training our first machine learning model here, people. This is very exciting, even if it's only step by step and it's only a small model. This is very important. Loss is going down again. Values are getting closer to where they should be. Again, we won't really know where they should be in real problems, but for now we do. So let's just...
3601, let's just... Loss is going
get excited. The real way to sort of measure your model's progress in practice is a lower loss value. Remember, lower is better. A loss value measures how wrong your model is. We're going down. We're going in the right direction. So that's what I meant by, as long as your values are going in the similar direction, so down, we're writing similar code here, but if your values are slightly different in terms of the exact numbers, don't worry too much because that's inherent to the randomness of machine learning, because the steps that the optimizer are taking are inherently random, but they're sort of pushed in a direction. So we're doing gradient descent here. This is beautiful. How low can we get the loss? How about we try to get to 0.1? Look at that, we're getting close to 0.1. And then, I mean, we don't have to do this hand by hand. Oh, the bias is getting close to where it exactly should be. We're below 0.1, beautiful. So that was only about, say, 10 passes through the data, but now you're seeing it in practice. You're seeing it happen. You're seeing gradient descent. Let's go, gradient descent, work in action. We've got images. This is what's happening. We've got our cost function, J.
The weight is supposed to be
A is another term for cost function, which is also our loss function. We start with an initial weight. What have we done? We started with an initial weight, this value here.
0.3.
And what are we doing? We've measured the gradient. Pytorch has done that behind the scenes for us. Thank you, Pytorch. And we're taking steps towards the minimum. That's what we're trying to do. If we minimize the gradient of our weight, we minimize the cost function, which is also a loss function. We could keep going here. for hours and get as low as we want. But my challenge for you, or actually, how about we make some predictions with our model we've got right now? Let's make some predictions. So with torch.inference mode, we'll make some predictions together, and then I'm going to set you a challenge. How about you run this code here for 100 epochs after this video, and then you make some predictions and see how that goes. So ypreds, remember how poor our predictions are? Ypreds new equals, we just do the forward pass here, model 0 on the test data. Let's just remind ourselves quickly of how poor our previous predictions were. Plot predictions, predictions equals y. Do we still have this saved? Ypreds. Hopefully this is still saved. There we go, shocking predictions. But we've just done 10 or so epochs, so 10 or so training steps. Have our predictions, do they look any better? Let's run this. We'll copy.
I can't call numpy on tensor that requires grat. Use tensor or detach.numpy instead. Oh, okay, because this is a quark, we have already fed everything else. Oh, another typo. What am I doing? Gotta get those right. Can't call numpy on tensor.
This, so 10 or plot predictions, predictions equals y. Do we still have this saved? Ypreds. Hopefully this is still saved. There we go, shocking prediction.
I wonder what's happening there. Let's see. That requires grad. Okay. And what about when we used to call it before? Okay, sorry. Yeah, inference, when we open it up in inference mode, it get rid of grat. So let's call that first and then use the predictions given by that to plot in the graph. That should work. So where was I? Yeah, I have to write the step here. Let's just insert another code block here. It's not a text block. I need to, well, let's delete this one. No, I want you to insert another one. I mean, yeah, I can't see, I wouldn't be able to see the earlier predictions anyway since I updated the model. Anyhow, let's just plot it with, you know what, let's just write it up here with, not with open, with torch dot inference. It's called inference
But we've just done ypreds.
Yep, it's called inference mod. Inference mod. Let's just do. Yeah, we overrode the predictions. Let's just call it ypreds new as is shown in the video or the tutorial. Now let's just call it on our test set and then plot the predictions on let's see. Let me turn on the light. It's getting, not the fan, the light. And gosh, I need to get a new cooling system. It's if I turn on the fan, then my mic won't be able to hear anything at all really. Anyhow, so we have a oh, there we go. I could swear that it was like here and now it's reached here.
Hopefully this is still saved. There we go, shocking predictions. But we've just done 10 or so epochs, so 10 or so training steps. Have our predictions, do they look any better? Let's run this. We'll copy this code. You know my rule, I don't really like to copy code, but in this case, I just want to exemplify a point. I like to write all the code myself. What do we got? Ypreds new. Oh, look at that. Look at that. We are moving our predictions closer. The red dot's closer to the green dots. This is what's happening. We're reducing the loss. In other words, we're reducing the difference between our model's predictions and our ideal outcomes through the power of backpropagation and gradient descent. So this is super exciting. We're training our first machine learning model. My challenge to you is to run this code here, change epochs to 100, see how low you can get this loss value, and run some predictions, plot them, and I think it's time to start testing. So give that a go yourself, and then we'll write some testing code in the next video.
All right. You know what? Let's just do 100 epochs and see where our plot, you know, what happens to our plot. It's plotted after we run this. Yeah, it's just missing 0.09 approximately, around that, and we need to subtract 3. But anyhow, here goes. We are so close now. If we run it for what happens if we run it for 1,000 times? Oh, it's continuing to be run. The loss is getting as tiny as ever. And okay, we're literally like near now. It should be almost touching the green points now. There we go.
I'll see you
That's
there.
it, people. I've written my first Mel model.
Welcome back. In the last video, we did something super excited. We saw our loss go down. So the loss is, remember, how different our model's predictions are to what we'd ideally like them. And we saw our model update its parameters through the power of backpropagation and gradient descent, all taken care of behind the scenes for us by Pytorch. So thank you, Pytorch. And again, if you'd like some extra resources on what's actually happening from a math perspective for backpropagation and gradient descent, I would refer to you to these. Otherwise, this is also how I learn about things. Gradient descent. There we go. How does gradient descent work? And then we've got backpropagation. And just to reiterate, I am doing this, just Googling these things, because that's what you're going to do in practice. You're going to come across a lot of different things that aren't covered in this course. And this is seriously what I do day to day as a machine learning engineer if I don't know what's going on. I just go to Google, read, watch a video, write some code, and
I think
then
most of software engineering as a whole is just Googling stuff. I can tell from experience in the work that I used to do. I used to be in.
I build my own intuition for it. But with that being said, I also issued you the challenge of trying to run this training code for 100 epochs. Did you give that a go? I hope you did. And how low did your loss value get? Did the weights and bias get anywhere close to where they should have been? How did the predictions look? Now, I'm going to save that for later on, running this code for 100 epochs. For now, let's write some testing code. And just a note, you don't necessarily have to write the training and testing loop together. You can functionize them, which we will be doing later on. But for the sake of this intuition building and code practicing and first time we're writing this code together, I'm going to write them together. So testing code, we call model.eval. What does this do? So this turns off different settings in the model not needed for evaluation/testing. This can be a little confusing to remember when you're writing testing code, but we're going to do it a few times until it's habit. So just make it a habit. If you're training your model, call model.train to make sure it's in training mode. If you're testing or evaluating your model, so that's what eval stands for, evaluate, call model.eval. So a few times in different settings in the model not needed for evaluation/testing. This can be a little confusing to remember when you're writing testing code, but we're going to do it a few times until it's habit. So just make it a habit. If you're training your model, call model.train to make sure it's in training mode. If you're testing or evaluating your model, so that's what eval stands for, evaluate, call model.eval. So it turns off different settings in the model not needed for evaluation/testing. This is things like dropout. We haven't seen what dropout is, /batch norm layers. But if we go into torch.nn, I'm sure you'll come across these things in your future machine learning endeavors. So dropout layers, there we go, and batch norm, do we have batch? Batch norm, there we go. If you'd like to work out what they are, feel free to check out the documentation. Just take it from me for now that model.eval turns off different settings not needed for evaluation and testing. Then we set up with torch.inference mode. Inference mode. So what does this do? Let's write down here. So this turns off gradient tracking. So as we discussed, if we have parameters in our model, and it turns off actually a few more things, and a couple more things behind the scenes, these are things, again, not needed for testing. So we discussed that if parameters in our model have requires grad equals true, which is the default for many different parameters in Pytorch, Pytorch will, behind the scenes, keep track of the gradients of our model and use them in loss.backward and optimizer step for backpropagation and gradient descent. However, we only need those two, backpropagation and gradient descent, during training, because that is when our model is learning. When we are testing, we are just evaluating the parameters, the patterns that our model has learned on the training data set. So we don't need to do any learning when we're testing. So we turn off the things that we don't need. And is this going to have the correct spacing for me? I'm not sure. We'll find out. So we still do the forward pass. in testing mode, do the forward pass. And if you want to look up Torch inference mode, just go Torch inference mode. There's a great tweet about it that Pytorch did, which explains what's happening. I think we've covered this before, but yeah. Want to make your inference code in Pytorch run faster? Here's a quick thread on doing exactly that. So inference mode is Torch no-grad. Again, you might see Torch no-grad. I think I'll write that down just to let you know. But here's what's happening behind the scenes. A lot of optimization code, which is beautiful.
Alright, let's search for it and see for ourselves. Inference mode. Actually, let's just search it on this browser. Inference mode Pytorch Twitter. It's like Google reads my mind with its auto suggestion. Okay, let's see. Oh, of course, it's not Twitter anymore, it's X. Alright, anyhow. I want to make your inference code in Pytorch run faster. Here's a quick thread on doing exactly that. Replace torch.nograd with the torch.inference mode context manager. Okay, but what does it do? Hey, give me more details. I could swear that the tutorial showed me a longer tweet. Maybe it's this one. Okay, so they did it in chunks, I guess. Anyhow, while nograd excludes operations from being tracked by autograd, yep, inference mode takes that 2 steps ahead, potentially speeding up your code depending on model complexity and hardware. Maybe this is what it does. Anyhow, what it means is our code becomes faster, and we should use that when we go into testing mode. That's what I'm gonna take out.
Beautiful. This is why we're using Pytorch, so that our code runs nice and fast. Then we go there. You may also see with torch.nograd in older Pytorch code. It does similar things, but inference mode is the faster way of doing things, according to the thread, and according to, there's a blog post attached to there as well, I believe. So you may also see torch.nograd in older Pytorch code, which would be valid, but again, inference mode is the better way of doing things. So do forward pass. So let's get our model. We want to create test predictions here. So we're going to go model 0. There's a lot of code going on here, but I'm going to just step by step it in a second. We'll go back through it all. And then number 2 is calculate the loss. Now, we're doing the test predictions here. Calculate the loss. Test predictions with model 0. So now we want to calculate the what? We want to calculate the test loss. So this will be our loss function, the difference between the test pred and the test labels. That's important. So for testing, we're working with test data. For training, we're working with training data. Model learns patterns on the training data, and it evaluates those patterns that it's learned, the different parameters on the testing data. Data it has never seen before. Just like in a university course, you'd study the course materials, which is the training data, and you'd evaluate your knowledge on materials you'd hopefully never seen before, unless you sort of were friends with your professor, and they gave you the exam before the actual exam. That would be cheating, right? So that's a very important point for the test data set. Don't let your model see the test data set before you evaluate on it. Otherwise, you'll get poor results. And that's print out what's happening. Epoch, we're going to go epoch, and then I will introduce you to my little jingle to remember all of these steps, because there's a lot going on. Don't you worry. I know there's a lot going on. But, again, with practice, we're going to know what's happening here like it's the back of our hand. All right. So, do we need this? Oh, yeah, we could say that. Oh, no, we don't need test here. Loss. This is loss, not test. Print out what's happening. Okay. And we don't actually need to do this every epoch. We could just go, say, if epoch divided by 10 equals 0, print out what's happening. Let's do that. Rather than clutter everything up, print it out, and we'll print out this.
Epoch modulus. Okay, we're printing it for every 10th training loop. Okay, anyhow, test loss. So loss is gonna be our calculated loss with the training data, and test loss is gonna be the loss for the testing data. What did I do? Yeah. Okay. Great. Yeah, let's add that if statement too. Then we're gonna print the values right after it. And let's just set our model back to the way it was. I think you need to save to save the model, right? So we're not gonna do that. We're gonna just create a new instance of our model. let's go back and create our reinstantiate our model rather. Let's just also do this, set up the loss function and optimizer.
Let's just step through what's happening. We've got 100 epochs. That's what we're about to run. 100 epochs. Our model is trained for about 10 so far, so it's got a good base. Maybe we'll just get rid of that base. Start a new instance of our model.
Aha, he did what
So we'll come right back down.
did.
So our model is back to randomly initialized parameters, but of course, randomly initialized, flavored with a random seed of 42. Lovely, lovely. And so we've got our training code here. We've discussed what's happening there. Now we've got our testing code. We call model.eval, which turns off different settings in the model not needed for evaluation/testing. We call with Torch inference mode context manager, which turns off gradient tracking and a couple more things behind the scenes to make our...
Let's take it a step further and also, you know, call our... So we can visually see it, you know. I mean, plot the predictions. Copy that. And the predictions is gonna be... copy... We're gonna put test spread over here.
code faster. We do the forward pass.
Actually, can we do that? Yeah, we can do that, of course, yeah.
We do the test predictions. We pass our model the test data, the test features to calculate the test predictions. Then we calculate the loss using our loss function. We can use the same loss function that we used for the training data, and it's called the test loss because it's on the test data set. And then we print out what's happening because we want to know what's happening while our model...
Oh, it's my camera. I just realized it right now. My camera is invisible, isn't it? Just like it died out. Gonna keep it for charging. Oh no, it didn't die out necessarily. It's still there. I need to change the sleep on this thing, you know. Maybe can't use apps due to device overheating. Okay, something we need to resolve. Looks like you know, it really takes the
model's training. We don't necessarily...
Yeah, we need another webcam and have one delivered today. But for the time being, let's just stick to this. Now how do I... Okay, let me just copy the URL and just put it here. If not, I will just do another video ninja. Scan a QR code. Opening. Guess you can say that worked. Let's see whether that worked or not. Moment of truth. And maybe it did not. Oh, maybe it's loading. I needed that confirmation, I believe. And there we miss. We don't need to capture our audio now. And yeah, there we go. Looks much better with the lights on. Okay. Anyhow, let's continue.
Necessarily have to do this, but the beauty of Pytorch is you can use basic Python printing statements to see what's happening with your model. And so, because we're doing 100 epochs, we don't want to clutter up everything here, so we'll just print out what's happening every 10th epoch. Again, you can customize this as much as you like what's printing out here. This is just one example. If you had other metrics here, such as calculating model accuracy, we might see that later on, hint, hint, we might print out our model accuracy. So this is very exciting. Are you ready to run 100 epochs? How low do you think our loss can go? This loss was after about 10, so let's just save this here. Let's give it a go. Ready? 3, 2, 1, let's run. Oh my goodness, look at that. Weights. Here we go. Every 10 epochs, we're printing out what's happening. So the 0th epoch, we started with losses 312. Look at it go down. Yes, that's what we want. And are our weights and bias, are they moving towards our ideal weight and bias values of 0.7 and 0.3? Yes, they're moving in the right direction here. The loss is going down. Epoch 20, wonderful. Epoch 30, even better. 40, 50, going down, down, down. Yes, this is what we want. This is what we want. Now, we're predicting a straight line here. Look how low the loss gets. After 100 epochs, we've got about 3 times less than what we had before. And then we got these values are quite close to where they should be. 05629, 03573. We'll make some predictions. What do they look like? YPRED's new. This is the original predictions with random values. And if we make YPRED's new, look how close it is after 100 epochs. Now, what's our, do we print out the test loss? Oh no, we're printing out loss as well. Let's get rid of that. I think this is this, yeah, that's this statement here. Our code would have been much cleaner if we didn't have that, but that's all right. Life goes on. So our test loss, because this is the test predictions that we're making, is not as low as our training loss. I wonder how we could get that lower. What do you think we could do? We just trained it for...
Our test loss is not as low as our... that's right. So maybe our model is just... Yeah, it's not as
longer. And what happened? How do you think you could get these red dots to line up with these green dots? Do you think you could? So that's my challenge to you for the next video. Think of something that you could do to get these red dots to match up with these green dots. Maybe train for longer. How do you think you could do that? That you could do to line up with these. What do you think we could do? We just trained it for longer, and what happened? How do you think you could get these red dots to line up with these green dots? Do you think you could?
I don't understand what the challenge is, but I guess that's, I mean, if he just wants to put the lines closer rather than using the test predictions, you can use the training predictions.
So that's my challenge to you for the next video. Think of something that you could do to get these red dots to match up with these green dots. Maybe train for longer. How do you think you could do that? So give that a shot, and I'll see you in the next video. We'll review what our testing code is doing. I'll see you there. Welcome back. In the last video, we did something super exciting. We trained our model for 100 epochs, and look how good the predictions got. But I finish it off with challenging you to see if you could align the red dots with the green dots. And it's okay if you're not sure how the best way to do that. That's what we're here for. We're here to learn what the best way to do these things together. But you might have had the idea of potentially training the model for a little bit longer. So how could we do that? Well, we could just rerun this code. So the model's going to remember the parameters that it has from what we've done here. And if we rerun it, well, it's going to start from where it finished off, which is already pretty good for our data set. And then it's going to try and improve them even more. This is, I can't stress enough, like what we are doing here is going to be very similar throughout the entire rest of the course for training more and more models. So this step that we've done here for training our model and evaluating it is seriously like the fundamental steps of deep learning with Pytorch, is training and evaluating a model. And we've just done it. Although, albeit to predict some red dots and green dots, that's all right. So let's try to line them up, hey? Red dots onto green dots. I reckon if we train it for another 100 epochs, we should get pretty darn close. You ready? 3, 2, 1. I'm going to run this cell again. Runs really quick because our data's nice and simple. But look at this. Last, we start at 0244. Where do we get down to? 008. Oh my goodness. So we've improved it by another 3x or so. And now this is where our model's got really good. On the test loss, we've gone from 0564. And we've gone down to 005. So almost 10x improvement there. And so we make some more predictions. What are our model parameters? Remember the ideal ones here. We won't necessarily know them in practice, but because we're working with a simple data set, we know what the ideal parameters are. Model 0 state tick weights. These are what they previously were. What are they going to change to? Oh, would you look at that? 06990. Now, again, if yours are very slightly different to mine, don't worry too much. That is the inherent randomness of machine learning and deep learning. Even though we set a manual seed, it may be slightly different. The direction is more important. So if your number here is not exactly what mine is, it should still be quite close to 0.7. And the same thing with this one. If it's not exactly what mine is, don't worry too much. The same with all of these loss values as well. The direction is more important. So we're pretty darn close. How do these predictions look? Remember, these are the original ones. We started with random, and now we've trained a model. Oh, so close. So close to being exactly that. So a little bit off. But that's all right. We could tweak a few things to improve this, but I think that's well and truly enough for this example purpose. You see what's happened. Of course, we could just create a model and set the parameters ourselves manually, but where would be the fun in that? We just wrote some machine learning code to do it for us through the power of backpropagation and gradient descent. Now, in the last video, we wrote the testing loop. We discussed a few of the steps here, but now let's go over it with a colorful slide, hey? Because, I mean, code on a page is nice, but colors are even nicer. Oh, we haven't done this. We might set up this in this video too. But let's just discuss what's going on. Create an empty list for storing useful value. So this is helpful for tracking model progress. How about we just do this right now, hey? We'll go here, and we'll go... So what did we have? Epoch count equals that, and then we'll go loss values. So why do we keep track of these? It's because if we want to monitor our model's progress, this is called tracking experiments. So track different values. If we wanted to try and improve upon our current model with a future model, so our current results, such as this, if we wanted to try and improve upon it, we might build an entire another model and we might train it in a different setup. We might use a different learning rate. We might use a whole bunch of different settings. But we track the values so that we can compare future experiments to past experiments, like the brilliant scientists that we are. And so where could we use these lists? Well, we're calculating the loss here, and we're calculating the test loss here. So maybe we, each time, append what's going on here as we do a status update. So epoch count dot append, and we're going to go the current epoch, and then we'll go loss values dot append the current loss value, and then we will do test loss values dot append the current test loss values. Wonderful. And now let's reinstantiate our model so that it starts from fresh. So this is just create another instance. So we're just going to reinitialize our model parameters to start from 0. If we wanted to, we could functionize all of this so we don't have to go right back up to the top of the code. But just for demo purposes, we're doing it how we're doing it. And I'm going to run this for, let's say, 200 epochs, because that's what we ended up doing, right? We ran it for 200 epochs because we did 100 epochs twice. And I want to show you something beautiful, one of the most beautiful sights in machine learning. So there we go, we run it for 200 epochs. We start with a fairly high training loss value and a fairly high test loss value. So remember, what is our loss value? It's MAE. So if we go back up to the top of the code, but just for demo purposes, we're doing it how we're doing it. And all of this so we don't have to create another instance. So we're just going to reinitialize. And now let's reinstantiate values dot append the current test loss values. Wonderful. And now let's reinstantiate our model so that it starts from fresh. So this is just create another instance. So we're just going to reinitialize our model parameters to start from 0. If we wanted to, we could functionize all of this so we don't have to go right back up to the top of the code. But just for demo purposes, we're doing it how we're doing it. And I'm going to run this for, let's say, 200 epochs, because that's what we ended up doing, right? We ran it for 200 epochs because we did 100 epochs twice. And
are you printing the thing?
Go right back up to the top. Reinitialize our model parameters to start from 0. If we wanted to, that it's the current test loss values. Wonderful. And now let's reinstantiate our model so that it starts from fresh. So this is just create another instance. So we're just going to reinitialize our model parameters to start from 0. If we wanted to, we could functionize all of this so we don't have to go right back up to the top of the code. But just for demo purposes, we're doing it how we're doing it. And I'm going to run this for, let's say, 200 epochs, because that's what we ended up doing, right? We ran it for 200 epochs because we did 100 epochs twice. And I want to show you something beautiful, one of the most beautiful sights in machine learning. So there we go, we run it for 200 epochs. We start with a fairly high training loss value and a fairly high test loss value. So remember, what is our loss value? It's MAE. So if we go...
Never mind. Append. Okay. Let's just reset those two code blocks. And we're gonna run this. Let's get rid of the other print statement. Oh yeah, let's get rid of this, and there we go.
Back. Yeah, this is what we're measuring for loss. Yeah. So this means for the test loss, on average, each of our dot points here, the red predictions, are 0.481. That's the average distance between each dot point. And then ideally, what are we doing? We're trying to minimize this distance. That's the MAE. So the mean absolute error. And we get it right down to 0.05. And if we make predictions, what do we have here? We get very close to the ideal weight and bias, make our predictions, Have a look at the new predictions. Yeah, very small distance here. Beautiful. That's a low loss value. Ideally, they'd line up, but we've got as close as we can for now. So this is one of the most beautiful sites in machine learning. So plot the loss curves. So let's make a plot, because what were we doing? We were tracking the value of epoch count, loss values, and test loss values. Let's have a look at what these all look like. So epoch count goes up, loss values ideally go down. So we'll get rid of that. We're going to create a plot, plt.plot. We're going to step back through the test loop in a second with some colorful slides. Label equals train loss. And then we're going to go plot. You might be able to tell what's going on here. Test loss values.
Alright, but let's just view our values here. Epoch count. Count. I think we just called the epoch count, didn't we? Test loss values and loss values. Count increases, loss and test loss value should decrease. Yeah, there we go. Perfect. And what we are gonna do next is plot the curves, right? So let's do that. I'm gonna plot the epoch count, the train loss values.
We're going to visualize it, because that's the Data Explorer's motto. It doesn't really work very well, and I don't visualize. This is...
Let's slip up what to do. Yeah, never mind. Delete that. I'm gonna label this as train loss.
equals... See, Colab does this autocorrect that doesn't really work very well, and I don't know when it does it and why it does it. Have we got... Oh no, we didn't say loss value. So that's a good autocorrect. Thank you, Colab. So training and loss and test loss curves. So this is another term you're going to come across often, is a loss curve. Now you might be able to think about a loss curve. If we're doing a loss curve,
Training and test loss curves.
and it's starting at the start of training, what do we want that curve to do? What do we want our loss value to do? We want it to go down. So what should an ideal loss curve look like? Well, we're about to see a couple. Let's have a look. Oh, what have we got wrong?
Like this,
We need to... Oh, turn...
should go down. Like as the number of epochs increases, the test loss should go down, so it should look something like that. Yeah, let's see. Plot.x label is gonna be epochs, but xbox epochs.
Wrong. Loss values? Why are we getting an issue? Test loss values? Ah, it's because they're all tensor values. So, I think we should... I might change this to numpy. Oh, can I just do that? If I just call this as a numpy array, we're going to try and fix this on the fly, people. Numpy array. Will this turn this into a numpy array? Let's see if we get numpy. We're figuring these things out together. Numpy as numpy. Because matplotlib works with numpy. Yeah, there we go. So, can we do loss values? Maybe... I'm going to try one thing, torch.tensor, loss values, and then call CPU.numpy. See what happens here. There we go. Okay, so let's just copy this. So what we're doing here is our loss values are still on Pytorch, and they can't be.
Yeah, and it needs to be in CPU too. Okay, gotcha. So we're gonna import numpy as np, and we're gonna call np.array torch.tensor loss values dot. We're gonna put that onto the CPU, but mine should already be on the CPU. I don't think I need it. Dot numpy, and we're gonna do the same for the other next function, which is our test loss values. Wait, why did I bring Copilot up? Test loss values, and that should work. There we go.
Because matplotlib works with
Right.
NumPy.
Let's
And so what we're doing here is
So this is our training loss and this is our test loss. So initially the test loss, of course the test loss would be higher than the training loss, decreases and then reaches the same level here, and our test loss actually becomes smaller than our training loss, which is
we're converting our loss values of the training loss to NumPy. And if you recall from the fundamentals section, we call CPU and NumPy. I wonder if we can just do straight up NumPy. Because we're not working on the... Yeah, okay. We don't need CPU because we're not working on the GPU yet, but we might need that later on. Will this work? Beautiful. There we go. One of the most beautiful sights in machine learning is a declining loss curve. So this is how we keep track of our experiments. Or one way, quite rudimentary. We'd like to automate this later on, but I'm just showing you one way to keep track of what's happening. So the training loss curve is going down here. The training loss starts at 0.3, and then it goes right down. The beautiful thing is they match up. If there was a too big a distance behind the train loss and the test loss, or sorry, between, then we're running into some problems. But if they match up closely at some point, that means our model is converging and the loss is getting as close to zero as it possibly can. If we train for longer, maybe the loss will go almost basically to zero. But that's an experiment I'll leave you to try, to train that model for longer. Let's just step back through our testing loop to finish off this video. So we did that. We created empty lists for strong useful values, storing useful values, strong useful values. Told the model what we want to evaluate, or that we want to evaluate. So we put it in evaluation mode. It turns off functionality used for training, but not evaluation, such as dropout and batch normalization layers. If you want to learn more about them, you can look them up in the documentation. Turn on Torch inference mode. So this is for faster performance. So we don't necessarily need this, but it's good practice. So I'm going to say that, yes, turn on Torch inference mode. So this disables functionality such as gradient tracking for inference.
Actually, we do need it, don't we? If you want to, well, for my use case, I need it because I'm plotting it, right? I think it was when I plotted it that it gave me the error.
Gradient tracking is not needed for inference, only for training. Now we pass the test data through the model. So this will call the model's implemented forward method. The forward pass is the exact same as what we did in the training loop, except we're doing it on the test data. So big notion there, training loop, training data, testing loop, testing data. Then we calculate the test loss value, how wrong the model's predictions are on the test data set. And of course, lower is better. And finally, we print out what's happening so we can keep track of what's going on during training. We don't necessarily have to do this. You can customize this print value to print out almost whatever you want because Pytorch is basically very beautifully interactive with pure Python. And then we keep track of the values of what's going on in epochs and train loss and test loss. We could keep track of other values here, but for now we're just going, okay, what's the loss value at a particular epoch for the training set and for the test set? And of course, all of this could be put into a function, and that way we won't have to remember these steps off by heart. But the reason why we've spent so much time on this is because we're going to be using this training and test functionality for all of the models that we build throughout this course. So give yourself a pat on the back for getting through all of these videos. We've written a lot of code, we've discussed a lot of steps, but if you'd like a song to remember what's happening, let's finish this video off with my unofficial Pytorch optimization loop song. So, for an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step. No, you only have to call this once, but now let's test. Call model.eval with Torch inference mode, do the forward pass, calculate the loss, and the real song goes for another epoch, because you keep going back through, but we finish off with print out what's happening, and then of course, we evaluate what's going on. With that being said, it's time to move on to another thing. But if you'd like to review what's happening, please, please, please try to run this code for yourself again and check out the slides and also check out the extra curriculum. Oh, by the way, if you want a link to all of the extra curriculum, just go to the book version of the course and it's all going to be in here. So that's there ready to go. Everything I link as extra curriculum will be in the extra curriculum of each chapter. I'll see you in the next video.
All right.
Welcome back. In the last video, we saw how to train our model and evaluate it by not only looking at the loss metrics and the loss curves, but we also plotted our predictions and we compared them. Hey, have a go at these random predictions. Quite terrible. But then we trained a model using the power of backpropagation and gradient descent, and now look at our predictions. They're almost exactly where we want them to be. And so you might be thinking, well, we've trained this model and it took us a while to write all this code to get some good predictions. How might we run that model again? So I've taken a little break after the last video, but now I've come back and you might notice that my Google Colab notebook has disconnected. So what does this mean? If I was to run this, is it going to work? I'm going to connect to a new Google Colab instance. But will we have all of the code that we've run above? You might have already experienced this if you took a break before and came back to the videos. So plot predictions is no longer defined. And do you know what that means? That means that our model is also no longer defined. So we would have lost our model. We would have lost all of that effort of training. Now, luckily, we didn't train the model for too long, so we can just go runtime, run all, and it's going to rerun all of the previous cells and be quite quick because we're working with a small data set and using a small model. But we've been through all of this code. Oh, what have we got wrong here? Model 0 state dict. Oh, that's all right. This is good. We're finding errors. So if you want to as well, you can just go run after. It's going to run all of the cells after. Beautiful. And we come back down. There's our model training. We're getting very similar values to what we got before. There's the loss curves. Beautiful. Still going. Okay, now our predictions are back because we've rerun all the cells and we've got our model here. So what we might cover in this video is saving a model in Pytorch. Because if we're training a model and you get to a certain point, especially when you have a larger model, you probably want to save it and then reuse it in this particular notebook itself. Or you might want to save it somewhere and send it to your friend so that your friend can try it out. Or you might want to use it in a week's time. And if Google Colab is disconnected, you might want to be able to load it back in somehow. So now let's see how we can save our models in Pytorch. So I'm going to write down here. There are 3 main methods you should know about for saving and loading models in Pytorch. Because, of course, with saving comes loading. So we're going to, over the next 2 videos, discuss saving and loading. So one is torch.save. And as you might guess, this allows you to save a Pytorch object in Python's pickle format. So you may or may not be aware of Python pickle. There we go. Python object serialization. There we go. So we've got the pickle module implements a binary protocols or implements binary protocols for serializing and deserializing a Python object. So serializing means I understand it as saving, and deserializing means that is loading. So this is what Pytorch uses behind the scenes, which is from pure Python. So if we go back here in Python's pickle format, number 2 is torch.load, which you might be able to guess what that does as well. Allows you to load a saved Pytorch object. And number 3 is also very important, is torch.nn.module.load_state_dict. Now, what does this allow you to do? Well, this allows you to load a model's saved dictionary, or saved state dictionary. Yeah, that's what we'll call it. Saved state dictionary. Beautiful. And what's the model state dict? Well, let's have a look. Model 0.state_dict. The beauty of Pytorch is that it stores a lot of your model's important parameters in just a simple Python dictionary. Now, it might not be that simple because our model, again, only has 2 parameters. In the future, you may be working with models with millions of parameters. So looking directly at the state dict may not be as simple as what we've got here. But the principle is still the same. It's still a dictionary that holds the state of your model. And so I've got these 3 methods. I want to show you where from, because this is going to be your extra curriculum, save and load models, your extra curriculum for this video. If we go into here, this is a very, very, very important piece of Pytorch documentation, or maybe even a tutorial. So your extra curriculum for this video is to go through it. Here we go. We've got torch save, torch load, torch module state dict. That's where, or load state dict. That's where I've got the 3 things that we've just written down. And there's a fair few different pieces of information. So what is a state dict? So in Pytorch, the learnable parameters, i.e. the weights and biases of a torch NN module, which is our model. Remember, our model subclass is NN module, are contained in the model's parameters. Access with model.parameters. A state dict is simply a Python dictionary object that maps each layer to its parameter tensor. That's what we've seen. And so then if we define a model, a Python dictionary object that maps each layer to its parameter tensor. That's what we've seen. And so then if we define a model, we can initialize the model, and if we wanted to print the state dict, we can use that. The optimizer also has a state dict, so that's something to be aware of. You can go optimizer.stateDict, and then you get an output here. And this is our saving and loading model for inference. So inference, again, is making a prediction. That's probably what we want to do in the future at some point. For now, we've made predictions right within our notebook, but if we wanted to use our model outside of our notebook, say in an application or in another notebook that's not this one, you'll want to know how to save and load it. So the recommended way of saving and loading a Pytorch model is by saving its state dict. Now, there's another method down here, which is saving and loading the entire model. So your extracurricular for this lesson, we're going to go through the code to do this, but your extracurricular is to read all of the sections in here and then figure out what the pros and cons are of saving and loading the entire model versus saving and loading just the state dict. So that's a challenge for you for this video. I'm going to link this in here. And now let's write some code to save our model. So Pytorch, save and load code. Code tutorial plus extra curriculum. So if we go saving our Pytorch model. So what might we want? What do you think the save parameter takes? If we have torch.save, what do you think it takes inside it? Well, let's find out together, hey? So let's import pathlib. We're going to see why in a second. This is Python's module for dealing with writing file paths. So if we wanted to save something to, this is Google Colab's files section over here. But just remember, if we do save this from within Google Colab, the model will disappear if our Google Colab notebook instance disconnects. So I'll show you how to download it from Google Colab if you want. Google Colab also has a way, save from Google Colab Google Colab to Google Drive to save it to your Google Drive if you wanted to, but I'll leave you to look at that on your own if you like. So we're first going to create a model directory. So create models directory. So this is going to help us create a folder over here called models. And of course we could create this by hand by adding a new folder here somewhere, but I like to do it with code. So model path, we're going to set this to path, which is using the path library here, to create us a path called models. Simple. We're just going to save all of our models to the models file. And then we're going to create model path. We're going to make that directory. Modelpath.mkdir for make directory. We're going to set parents to equals true. And we're also going to set exist OK equals to true. That means if it already existed, it won't throw us an error. It will try to create it, but if it already exists, it'll just recreate the parents directory or it'll leave it there. It won't error out on us. We're also going to create a model save path. This way, we can give our model a name. Right now, it's just model 0. We want to save it under some name to the models directory. So let's create the model name. Model name equals 01. I'm going to call it 01 for the section. That way, if we have more models later on in the course, we know which ones come from where. You might create your own naming convention. Model workflow, Pytorch workflow, model0.pth. And now, this is another important point. Pytorch objects usually have the extension .pth for Pytorch or .pt. So if we go in here, and if we look up .pt, yeah. A common convention is to save models using either a .pt or .pth file extension. I'll let you choose which one you like. I like .pth. So if we go down here, .pth, they both result in the same thing. You just have to remember to make sure you write the right loading path and right saving path. So now we're going to create a model save path, which is going to be our model path. And because we're using the path lib, we can use this syntax that we've got here, model path / model name. And then if we just print out model save path, what does this look like? There we go. So it creates us a POSIX path using the path lib library of models / 01 Pytorch workflow model 0.pth. We haven't saved our model there yet. It's just got the path that we want to save our model ready. So if we refresh this, we've got models over here. Do we have anything in there? No, we don't yet. So now is our step to save the model. So 3 is save the model state dict. Why are we saving the state dict? Because that's the recommended way of doing things. If we come up here, saving and loading the model for inference, save and load the state dict, which is recommended. We could also save the entire model, but that's part of your extra curriculum to look into that. So let's use some syntax that's quite like this. Torch.save, and then we pass it an object, and we pass it a path of where to save it. We already have a path. And good thing is we already have a model. So we just have to call this. Let's try it out. So let's go print f, saving model to, and we'll put in the path here, model save path. I like to print out some things here and there. That way we know what's going on. And, oh, I don't need that capital A, do I? Getting a little bit trigger happy here with the typing. So torch.save, and we're going to pass in the object parameter here. And if we looked up torch save, we can go, what does this code take? So torch save object f, what is f? A file like object. Okay. Or a string or OS path like object. Beautiful. That's what we've got. A path like object containing a file name. So let's jump back into here. The object is what? It's our model 0.stateDict. That's what we're saving. And then the file path is model save path. You ready? Let's run this and see what happens. Beautiful. Saving model to models sets our model path, and there's our model there. So if we refresh this, what do we have over here? Wonderful. We've saved our trained model. So that means we could, potentially, if we wanted to, you could download this file here. That's going to download it from Google Colab to your local machine. That's one way to do it. But there's also a guide here to save from Google Collaboratory to Google Drive. That way you could use it later on. So there's many different ways. The beauty of Pytorch.
Linear regression model has no attribute save dict. Oh, it's state dict, right? What did I put? I put save dict there. No, I spelled it wrong. Should be lowercase, not uppercase. There we go. Let's see. This is our. Can you open this? Ah, we can open this. Although that's just yeah, binary data. Alright, cool. Let me just minimize this.
Torch is its flexibility. So now we've got a saved model. Well, let's just check using our ls command. We're going to check models. Yeah, let's just check models. This is going to check here. So this is list. Wonderful. There's our 01 Pytorch workflow model 0.pth. Now, of course, we've saved a model. How about we try loading it back in and seeing how it works? So if you want a challenge, read ahead in the documentation and try to use torch.load to bring our model back in. See what happens. I'll see you in the next video. Welcome back. In the last video, we wrote some code here to save our Pytorch model. I'm just going to X out of this, a couple of things that we don't need just to clear up the screen. And now we've got our .pth file, because remember, .pth or .pt is a common convention for saving a Pytorch model. We've got it saved there, and we didn't necessarily have to write all of this path-style code, but this is just handy for later on if we wanted to functionize this and create it in, say, a save.py file over here, so that we could just call our save function and pass it in a file path where we want it to save, like a directory and a name, and then it'll save it exactly how we want it for later on. But now we've got a saved model. I issued a challenge of trying to load that model in.
Wait, I didn't do that, did I? So let's see. Learn. Why can't I spell? Learn. Pytorch.io. Let's see. I think we reached here, right? Let's load it using saving and loading models. What is a state dict? Yeah, in Pytorch, the learnable parameters, weights, and biases of a torch containing models parameters accessible. A state dict is simply a Python dictionary object that maps each layer to its parameter tensor. Alright, okay. Note that only layers with learnable parameters are registered buffers have entries in the model state dict. Optimizer objects also have a stated which contains information about the optimizer states as well as the hyperparameters used. Alright, okay, that was a mouthful. Then because state dict objects are Python dictionary, they can be easily saved, updated, altered, and restored, adding a great deal of modularity to Pytorch models and optimizers. Alright, enough theory. Let's see. Okay, that we just save the model and let's just write down the code to load this model. Loaded model, let's call it that. Loaded model is going to be, we're gonna create a model for linear regression, and then we are gonna load our save state dict using this, and inside we're gonna give it torch.load, and we're gonna give it the model save path, and yeah, we can just do model.giveval. It should be loaded model. Alright, okay, let's just do with torch.inference mod, and then we can just do loaded model. Well, just do test red dictions as loaded model with xtest, and then we can just call our functions plot predictions and give it our predictions, which is test data, not test data, test spreads. Let's also just print out our test loss. Test loss is going to be the loss function, and we have our y test and x test. Oh, sorry, not y test. Test spreads. And then we have what our output should be, which is y test. Right, this is, so I remember it, how we calculate the test loss. test spread and white test, and yep, there we go. So if we clear that typo and then load this, we should get, there we go, our loaded model. But if we do not load the model and just do this instead, we get something entirely off because it's not trained at all. Cool. Now let's load an entire model rather than just the state deck. Alright, let's do that. Torch.save and torch.load. Save. What's the difference then? Okay, I understand this. It's the same except we save more things, I guess. Let's just but I guess we can just see it in action right now, can't we? Along with this, also save it to let's call it entire model name. Let's add entire call that. Alright, should fix it, and let's do torch.save. Oh, we need to save the model now, huh? So we've already loaded the model, haven't we? I mean, we haven't overwritten the model or anything, like we haven't reconnected, so we can use model 0, and if we reopen this, that doesn't work because this isn't defined as path. This should be entire model save path, and there we go. So if I reopen this, I should have, let's look at the size difference. It's 1.53 kilobytes, and it's of course it is a bit more hefty in size. I just want to open this and see. Okay, let's just see what's the con on doing it this way then. Delete file, don't delete it. Alright, let's just load it too. Let's just let's just load the model using that way, which would be loaded model is just gonna be it's just gonna be, instead of doing torch.save, we just do torch.load entire model save path. The rest is the same, stays the same. Now let's see torch save versus state text. Yeah, oh, we have another one. What is torch script? I did see it here. One common way to do inference with a trained model is to use torch script, an intermediate representation of a Pytorch model. It can be run in Python as well as in a high performance environment like C++. Okay, that's TorchScript is actually the recommended model format for scale inference and deployment. Okay. Didn't know that. Saving and loading a general checkpoint from inference under resuming training. Alright, let's just look at a comparison now. Oh, we have we had a chat. Who's this? NCS07. I think he's gone now though. Yeah. Thank you, NCS, for viewing my stream. I didn't see your message there. Alright. Anyhow, let's get back to our what we were doing, Yeah, let's get back to our session. What I'm saying, yeah. So we were trying to see what's the pros and cons of this, right? So complete model saving, static saving. I seem to understand saving reducing the file size, yeah. While the con is that I have to recreate the model instance. Is that correct? Let's see, got it. Let's see. Yes, you will need to, but not that saving the amount requires you to exactly recreate the same file structure, including the source code of the model on the target system. Gotcha. The code needs to remain the same, like exactly the same. If I am to do it via the entire model method. But if it's just the state dict, then minor differences are fine. That's what I understood and I'm taking from it.
So do we have torch.load in here? Did you try that out? We've got a few options here. Wonderful, but we're using one of the first ones. So let's go back up here. If we wanted to check the documentation for torch.load, we've got this option here, load. What happens? Loads an object saved with torch.save from a file. Torch.load uses Python's unpickling facilities, but treats storages which underlie tensors specially. They are first deserialized on the CPU and then are moved to the device they were saved from. Wonderful. So this is moved to the device. If later on when we're using a GPU, this is just something to keep in mind. We'll see that when we start to use a CPU and a GPU. But for now, let's practice using the torch.load method and see how we can do it. So we'll come back here and we'll go loading a Pytorch model. And since just going to start writing here, since we saved our model's state dict, so just the dictionary of parameters from a model, rather than the entire model, we'll create a new instance of our model class and load the state dict, load the saved state dict, that's better, state dict, into that. Now, this is just words on a page. Let's see this in action. So to load in a state dict, which is what we saved, we didn't save the entire model itself, which is one option. That's extra curriculum, but we saved just the model state dict. So if we remind ourselves what model 0.state dict looks like, we saved just this. So to load this in, we have to instantiate a new class or a new instance of our linear regression model class. So to load in a saved state dict, we have to instantiate a new instance of our model class. So let's call this loaded model 0. I like that. That way we can differentiate because it's still going to be the same parameters as model 0, but this way we know that this instance is the loaded version, not just the version we've been training before. So we'll create a new version of it here, linear regression model. This is just the code that we wrote above, linear regression model. And then we're going to load the saved state dict of model 0. And so this will update the new instance with updated parameters. So let's just check before we load it. We haven't written any code to actually load anything. What does loaded model 0, what does the state dict look like here? It won't have anything. It'll be initialized with what? Oh, loaded. That's what I called it. Loaded. See how it's initialized with random parameters? So essentially all we're doing when we load a state dictionary into our new instance of our model is that we're going, hey, take the saved state dict from this model and plug it into this. So let's see what happens when we do that. So loaded model 0. Remember how I said there's a method to also be aware of up here, which is torch.nn_module.load state dict. And because our model is a what? It's a subclass of torch.nn.module. So we can call load state dict on our
This allows to load a model saved state.
A model directly or on our instance. It's a subclass of torch.nn.module. So we can call load state dict on our model directly, or on our instance. So recall, linear regression model is a subclass of nn.module. So let's call in load state dict, and this is where we call the torch.load method.
Oh, because torch. I see. I see what it
Of
is.
nn.module. So let's call in load state dict, and this is where we call the torch.load method, and then we pass it the model save path. Is that what we called it? Because torch.load, it takes in f. So what's f? A file-like object, or a string, or an OS path-like object. So that's why we created this path-like object up here, model save path. So all we're doing here, we're creating a new instance, linear regression model, which is a subclass of nn.module, and then on that instance, we're calling in load state dict of torch.load model save path, because what's saved at the model save path? Our previous model's state dict, which is here. So if we run this, let's see what happens. All keys match successfully. That is beautiful. And so see the values here? Loaded state dict of model 0. Well, let's check the loaded version of that. We now have, wonderful, we have the exact same values as above, but there's a little way that we can test this. So how about we go make some predictions? So make some predictions just to make sure with our loaded model. So let's put it in eval mode, because when you make predictions, you want it in evaluation mode, so it goes a little bit faster. And we want to also use inference mode. So with torch.inference mode for making predictions, we want to write this, loaded model preds. We're going to make some predictions on the test data as well. So loaded model 0, we're going to forward pass on the X test data, and then we can have a look at the loaded model preds. Wonderful. And then to see if the two models are the same, we can compare loaded model preds with original model preds. So Y preds, these should be equivalent. Equals loaded model preds. Do we have the same thing? False, false, false. What's going on here? Y preds. How much different are they? Oh, where's that happened? Have we made some model preds with this yet? So how about we make some model preds? This is troubleshooting on the fly team. So let's go model 0.eval, and then with torch.inference mode, this is how we can check to see that our two models are actually equivalent. Y preds equals, I have a feeling Y preds actually saved somewhere else, equals model 0, and then we pass it the X test data. And then we might move this above here, and then have a look at what Y preds equals. Do we get the same output? Yes, we should. Wonderful. Okay, beautiful. So now we've covered saving and loading models, or specifically saving the model's state dict. So we saved it here with this code, and then we loaded it back in with load state dict plus torch load, and then we check to see by testing equivalence of the predictions of each of our models. So the original one that we trained here, model 0, and the loaded version of it here. So that's saving and loading a model in Pytorch. There are a few more things that we could cover, but I'm going to leave that for extra curriculum. We've covered the two main things, or the three main things. 1, 2, 3. If you'd like to read more, I'd highly encourage you to go through and read this tutorial here. But with that being said, we've covered a fair bit of ground over the last few videos. How about we do a few videos where we put everything together, just to reiterate what we've done. I think that'll be good practice. I'll see you in the next video. Welcome back. Over the past few videos, we've covered a whole bunch of ground in a Pytorch workflow. Starting with data, then building a model. Well, we split the data, then we built a model. We looked at the model building essentials. We checked the contents of our model. We made some predictions with a very poor model because it's based off random numbers. We spent a whole bunch of time figuring out how we could train a model. We figured out what the loss function is. We saw an optimizer. We wrote a training and test loop. We then learned how to save and load a model in Pytorch. So now I'd like to spend the next few videos putting all this together. We're not going to spend as much time on each step, but we're just going to have some practice together so that we can reiterate all the things that we've done. So putting it all together, let's go back through the steps above and see it all in one place. Wonderful. So we're going to start off with 6.1. And we'll go have a look at our workflow. So 6.1 is data.
I think we should do this like continuously. I can see that my two time mark is approaching. So let's do one thing. I'm gonna take my 20-minute break now, and we'll come back, and then we can continue. Since this segment is gonna be a bit more lengthy than others. So yeah, that's what I'm gonna do. Stay tuned. I'll be back in 20 minutes. Be right back. Alright, as promised, I am back again. And let me switch to my... Oh no, I forgot to... I should have kept my phone for charging while I was gone. The things I do. Yep, my phone's dead. Well, that's on my part though. Should remind myself to do this again and again. Alright, for the timing we'll just keep it for charging as it is. See, is it even charging or is it just me just pressing random buttons? How do I keep it for charge? It should be charging. Give me a second. Let me just sort this thing out. Yeah, yes it is charging now. Alright, cool. Anyhow, let's just continue with our session. Midway I'll just turn on my camera. Geez, I need to buy a camera separately for this, don't I? Now where did I place my ear? Oh yeah, there we go. Alright, let's start, guys. Let me also turn on
State
my
dict.
desktop audio.
What do we got here? What are our weight and bias? Oh my gosh, so close. So we just set weight and bias before to be 0.7 and 0.3. So this is what our model has estimated our parameters to be based on the training data. 0.6968. That's pretty close to 0.7, nearly perfect. And the same thing with the bias, 0.3025 versus the perfect value is 0.03. But remember, imperfect parameter starts up here. Now let's run this. What's happening here? Hey, look at that. Wonderful.
I think we went... Yeah, I think the video was playing while I was gone or something.
Welcome back. In the last video, we set up some device agnostic code and we got ready to start putting everything we've learned together. So now let's continue with that. We're going to recreate some data. Now, we could just copy this code, but we're going to write it out together so we can have some practice creating a dummy data set. And we want to get to about this stage in this video. So we want to have some data that we can plot so that we can build a model to, once again, learn on the blue dots to predict the green dots. So we'll come down here, data. I'm going to get out of this as well so that we have a bit more room. Let's now create some data using the linear regression formula of y equals weight times features plus bias. And you may have heard this as y equals mx plus c or mx plus b or something like that, or you can substitute these for different names. Images, when I learned this in high school, it was y equals mx plus c. Yours might be slightly different. Yeah, bx plus a, that's what they use here. Whole bunch of different ways to name things, but they're all describing the same thing. So let's see this in code rather than formulaic examples. So we're going to create our weight, which is 0.7, and a bias, which is 0.3. These are the values we previously used. For a challenge, you could change these to 0.1 maybe, and 0.2. These could be whatever values you'd like to set them as. So weight and bias, the principle is going to be the same thing. We're going to try and build a model to estimate these values. So we're going to start at 0, and we're going to end at 1. So we can just create a straight line, and we're going to fill in those between 0 and 1 with a step of 0.02. And now we'll create the x and y features, x and y, which is features and labels actually. So x is our features and y are our labels. X equals torch.arange, and x is a capital. Why is that? Because typically x is a feature matrix. Even though ours is just a vector now, we're going to unsqueeze this so we don't run into dimensionality issues later on. You can check this for yourself. Without unsqueeze, errors will pop up. And y equals weight times x plus bias. You see how we're going a little bit faster now? This is sort of the pace that we're going to start going for things that we've already covered. If we haven't covered something, we'll slow down. But if we have covered something, I'm going to step it through. We're going to start speeding things up a little. So if we get some values here, wonderful. We've got some x values, and they correlate to some y values. We're going to try and use the training values of x to predict the training values of y, and subsequently for the test values. Oh, and speaking of training and test values, how about we split the data?
Again? Unsqueeze removes the... Or was it squeeze? I can't remember. What does unsqueeze do, Pytorch? Unsqueeze adds bracket and squeeze removes the bracket. You can think of it as bracket taking up space and squeeze just removes that space. Cool. Right, and yeah, because the range is a tensor and we just want to add another dimension to it. All right, perfect. Anyhow, let's create our formula, which is y is equal to m x plus c. M is gonna be our weight. Weight is basically our slope plus bias. Bias is gonna be our c for this case. Or usually the constant in y is equal to mx plus c. Not usually, it is the constant. We're just gonna print x and y are features and labels. Cool, there we go. So when x is 0, y is 3, x is 2, y is 3140, because 2 into 7, 14, we add that. Of course with the decimal point.
So let's split the data. Split data. So we'll create the train split equals int 0.8. We're going to use 80%, which is where 0.8 comes from, for the length of x. So we use 80% of our samples for the training, which is a typical training and test split, 80-20, thereabouts. You could use like 70-30, you could use 90-10. It all depends on how much data you have. There's a lot of things in machine learning that are quite flexible. Train split, we're going to index on our data here so that we can create our splits. Google Colab auto-corrected my code in a non-helpful way just then. And we're going to do the opposite split for the testing data. Now let's have a look at the lengths of these. If my calculations are correct, we should have about
Train split. It should be 40-50, right? That should be the split that's being made right now.
about 40 training samples and 10 testing samples.
Yep.
And again, this may change in the future. When you work with larger data sets, you might have 100,000 training samples and 20. thousand testing samples. The ratio will often be quite similar. And then let's plot what's going on here. So plot the data and note if you don't have the plot predictions function loaded, this will error. So we can just run plot predictions here if we wanted to, and we'll pass it in xtrain, ytrain, xtest, ytest, and this should come up with our plot. Wonderful. So we just recreated the data that we've been previously using. We've got blue dots to predict green dots. But if this function errors out because you've started the notebook from here,
So I can just do this.
right from this cell, and you've gone down from there, just remember, you'll
Because it's the same data, it's gonna be the same.
just have to go up here and copy this function. We don't have to do it because we've run all the cells, but if you haven't run that cell previously, you could put it here and then run it, and we'll get the same outcome here. Wonderful. So what's next? Well, if we go back to our workflow, we've just created some data. And have we turned it into tensors yet? I think it's just still, oh yeah, it is. It's tensors because we use Pytorch to create it.
Yeah.
But now we're up to building or picking a model. So we've built a model previously. We did that back in build model. So you could refer to that code and try to build a model to fit the data that's going on here. So that's your challenge for the next video. So building a Pytorch linear model. And why do we call it linear? Because linear refers to a straight line. What's non-linear? Non-straight. So
Yeah. Alright, so let's do that. We are gonna create our linear regression model, and this inherits from torch.nn dot, or is it torch.models.nn? I think so. Let's see. Torch.models.nn, or is it torch.nn models? Let's check. So it is torch.nn. Okay, it's not yeah. it's supposed to be n dot module. Actually, since we have not imported n as separate, we have to do torch dot n dot module, and let's just define our constructor here. What exactly is our constructor going to take? Nothing, in fact, right? And we just have to call our super coordinate right now. And we're gonna define our parameters. So self.weight is gonna be, let's use the docs. We won't check the code we've already wrote, but we are able to look into docs. Torch model. We want to create a parameter here. So what we're gonna do is we're gonna create torch. Is it para? Not really. Self.flat, no, that's not what happened. We just have to create a random parameter here. Guess I have to look into this guy's code after all. Oh, it's n dot parameter. Yeah, there we go. Yeah, n dot parameter. This is a module and this is a class. Okay, so this requires a tensor, for which we are gonna just give it a number. So basically nrand, right? A random number, or is it random? I think it's random. Random requires grad is gonna be true. It does require a gradient. D type is gonna be torch dot float. Great, that should do it. And then we have our self dot bias, which is gonna be the same thing, that is n dot parameter. Gonna create a random parameter, random number, and set requires grad as true, and then oh, the size, we need to specify the size of this, right? The size is just gonna be 1, and to make it pretty, I'm gonna do it on 3 separate lines. Same thing here, requires grad is set to true, and data type is also set to torch.float as we did for self.weight. Cool. So we have self.weight, self.bias, and since linear regression model is a subclass of torch.n.module, we need to give it a forward function. So we're going to define forward. Now forward would take an x, which is gonna be our tensor, Okay, maybe we don't highlight that. Okay, anyhow, what we're basically gonna do now is we're gonna return our actually what should we do for this one? We just define a function, right? Like what exactly do we, yeah, return self dot weights into x. We return our y here. X is gonna be a tensor torch dot tensor, and we are gonna return, well, let's just type out the formula. Y is equal to self dot y is equal to mx, this is gonna be our slope, times x plus c, and we're just gonna return y. That's gonna be self dot forward. Cool, that should be our model. Let's go back.
I'll see you in the next video. Give it a shot before we get there, but we're going to build a Pytorch linear model. Welcome back. We're going through some steps to recreate everything that we've done. In the last video, we created some dummy data, and we've got a straight line here. So now, by the workflow, we're up to building a model or picking a model. In our case, we're going to build one to suit our problem. So we've got some linear data, and I've put building a Pytorch linear model here. I issued you the challenge of giving it a go. You could do exactly the same steps that we've done in build model, but I'm going to be a little bit cheeky and introduce something new here, and that is the power of torch.nn. So let's see it. What we're going to do is we're going to create a linear model by subclassing nn.module, because why? A lot of PyTorch models subclass nn module. So class linear regression, what should we call this one? Linear regression model v2, how about that? And we'll subclass nn.module. So much similar code to what we've been writing so far, or when we first created our linear regression model. And then we're going to put the standard constructor code here, def init underscore underscore, and it's going to take as an argument self. And then we're going to call super dot another underscore init underscore underscore brackets. But we're going to, instead of, if you recall above, back in the build model section, we initialized these parameters ourselves. And I've been hinting at in the past, in videos we've seen before, that oftentimes you won't necessarily initialize the parameters yourself. You'll instead initialize layers that have the parameters inbuilt in those layers. We still have to create a forward method, but what we're going to see is how we can use a torch linear layer to do these steps for us. So let's write the code and then we'll step through it. So we'll go use nn.linear, because why? We're building a linear regression model and our data is linear, and in the past, our previous model has implemented the linear regression formula. So for creating the model parameters, so we can go self.linear layer equals, so this is constructing a variable that this class can use, self linear layer equals nn.linear. Remember, nn in Pytorch stands for neural network. And we have in features as one of the parameters and out features as another parameter. This means we want to take as input of size 1 and output of size 1. Where does that come from? Well, if we have a look at X train and Y train, we have one value of X, maybe there's too many here. X5 will be the first 5. 5 and 5. So recall, we have one value of X equates to one value of Y. So that means within this linear layer, we want to take as one feature, X, to output one feature, Y. And we're using just one layer here. So the input and output shapes of your model, in features, out features, what data goes in, and
but in multi-variable equations, it would be like 2 and out would be 1.
what data comes out, these values will be highly dependent on the data that you're working with. And we're going to see different data or different examples of input features and output features all throughout this course. So, but that is what's happening. We have one in feature to one out feature. Now, what's happening inside nn.linear? Let's have a look. Torch nn linear. We go to the document.
Let's check it ourselves first. Applies an affine. Okay, I don't understand what affine is, but a linear transformation to the incoming data. Y is equal to, fancy way of writing M. Okay, X plus C. Is this A transpose? Anyhow, on certain we will use different precision for backward. Okay. In feature size of each input sample, out feature size of each output sample. Bias. If set to false, the layer will not learn an additive bias. Oh, bias is just constant, okay? Default is true. Alright, anyhow. Oh, I understand. So by default, if we set this to false, bias will just be equivalent to 0. Okay. Input weight. The learnable weights. Okay, wait. Let's just read to this. Variables, weight and bias. The learnable weights of the module of shape. The values are initialized from the k is equal to 1 by in features. I didn't quite understand what this means, but yeah, anyhow. So basically this just creates our weight and bias for us. We just have to instantiate the layer is what I'm going to take away from this.
Documentation applies a linear transformation to the incoming data. Where have we seen this before? Y equals x a t plus b. Now they're using different letters, but we've got the same formula as what's happening up here. We've got the same formula as our data. Weight times x plus bias. And then if we look up linear regression formula once again, linear regression formula,
I'll turn my camera on.
we've got this formula here. Now,
50%.
again, these letters can be replaced by whatever letters you like, but this linear layer is implementing the linear regression formula that we created in our model before. So it's essentially doing this part for us. And behind the scenes, the layer creates these parameters for us. So that's a big piece of the puzzle of Pytorch, is that, as I've said, you won't always be initializing the parameters of your model yourself. You'll generally initialize layers, and then you'll use those layers in some forward computation. So let's see how we could do that. So we've got a linear layer, which takes us in features 1 and out features 1. What should we do now?
What it does is this layer creates the variables weight and bias for us. That's good.
Well, because we've subclassed nn.module, we need to override the forward method. So we need to tell our model what should it do as a forward computation. And in here, it's going to take itself as input, as well as x, which is conventional for the input data. And then we're just going to return here self.linearLayer x. Right, and actually we might use some typing here to say that this should be a torch tensor, and it's also going to return a torch.tensor. That's using Python's type hints. So this is just saying, hey, x should be a torch tensor, and I'm going to return you a torch tensor, because I'm going to pass x through the linear layer, which is expecting one in feature and one out feature, and it's going to this linear transform. That's another word for it. Again, Pytorch and machine learning in general has many different names for the same thing. I would call this linear layer. I'm going to write here, also called linear transform, probing layer, fully connected layer, dense layer in TensorFlow. So a whole bunch of different names for the same thing, but they're all implementing a linear transform. They're all implementing a version of linear regression. Y equals x, a transpose plus b. In features, out features. Wonderful. So let's see this in action. So we're going to go set the manual seed so we can get reproducibility.
What?
Linear regression. Y equals x, a transpose plus b. In features, out features. Wonderful.
Oh, okay,
so
right.
let's see this in action.
Alright, so here we had literally like wrote out the function. This is just a function of its own. What is the function, you ask? We go to the docs, we get the same function. So this method outputs y, which is x a raised to t plus b, and since we've set bias as true, it would also have bias for us. So we just have to give it x, and it returns this, and whatever value this function outputs, self.linear layer returns it to us.
So we're going to go set the manual seed so we can get reproducibility as well. Torch.manual seed. And we're going to set model 1 equals linear regression. This is model 1 because we've already got model 0, linear regression v2. And we're going to check model 1, and we're going to check its state dictionary. State dict. There we go. What do we have inside this? Ordered dict. Has that not created anything for us? Model 1 dot state dict. Ordered dict. We haven't got anything here. Linear regression model v2.
Wait, I'll figure that one out. Oh wait, it says and maybe I can't figure that one out. It, maybe something to do with the initializer perhaps. Wait, don't we have to train it at least one time, or maybe something like that?
Ideally, this should be outputting a weight and a bias. Yeah. variables, weight, and bias. Let's dig through our code line by line and see what we've got wrong. Did you notice this? The init function, so the constructor had the wrong amount of underscores, so it was never...
Well, but mine has the correct amount of underscores. Mine should give me the... Oh, maybe I didn't run it. Okay. So it's you, Daniel. Anyway. How do I delete this code block?
Never actually constructing this linear layer. Troubleshooting on the fly, team. There we go. Beautiful. So we have a linear layer, and it is created for us inside a weight and a bias. So effectively, we've replaced the code we wrote above for build model, initializing a weight and bias parameter with the linear layer. And you might be wondering why the values are slightly different, even though we've used the manual seed. This goes behind the scenes of how Pytorch creates its different layers. It's probably using a different form of randomness to create different types of variables. So just keep that in mind. And to see this in action, we have a conversion here. So this is what's going on. We've converted, this is our original model class, linear regression. We initialized our model parameters here. We've got a weight and a bias, but instead we've swapped this in our linear regression model V2, this should be V2, to use linear layer. And then in the forward method, we had to write the formula manually here when we initialized the parameters manually, but because of the power of torch.nn, we have just passed it through the linear layer, which is going to perform some predefined forward computation in this layer. So this style of what's going on here is how you're going to see the majority of your Pytorch deep learning models created using...
Alright people, we've hit our 8-hour mark. Okay, it's 1 day, 1 hour, but I would say we're about third of the way. Less than third of the way there, so we are making good progress.
Using pre-existing layers from the...
If you could see my face, you could see how happy I am right now. Speaking of face or camera, how's the percentage doing it? It's at 62%. What should I do? What should I do? You know what? Let me turn on my cam. First, let me turn on my phone for that. Okay, let that turn on. Yeah, I'll connect it in a bit. Let's just go
torch.nn module. So if we go back into torch.nn, we have a lot of different layers here. So we have convolutional layers, pooling layers, padding layers, normalization, recurrent, transformer, linear. We're using a linear layer, dropout, etc., etc. So for all of the common...
Take a look at some of those, torch.nn. What's up, con? I've been hearing this name for quite some time now. Applies a one-dimensional... Whoa, that's quite a lot of math. What about this? What formula does this use? What about this? Oh, maybe there's just different types of the same thing. Maybe this. Let's see. Alright, I'm pretty sure we'll come to that. I just...
layers in deep learning, because that's what neural networks are. They're layers of different mathematical transformations. Pytorch has a lot of pre-built implementations. So that's a little bit of a sneaky trick that I've done to alter our model, but we've still got basically the exact same model as we had before. So what's next? Well, is to train this model. So let's do that in the next video.
Yeah, and let me also turn on my camera now in that case. Alright, let me just set up my camera. I'm just gonna switch to the other screen for a bit so I can just take up my QR code. To set up the camera and all. Open lens. let's let me connect this. I think I can just close the QR code and just insert the link. Also mute it. Alright, there you go. My camera is back up again. Yep, there we go. Alright, cool. So let's continue the stream. Let's continue where we last left off. So we're gonna
Welcome back.
build
So in the last video, we built a
very
Pytorch
now
linear
are
model.
we?
Nice and simple, using a
Wait
single
a second, am I on the wrong? Yeah, I'm on the wrong overlay. That should be better.
nn.linear layer with one in feature, one out feature, and we overrid the forward method of nn.module using the linear layer that we created up here. So what's going to happen is when we do the forward pass on our model, we're going to put some data in and it's going to go through this linear layer, which behind the scenes, as we saw with torch nn linear, behind the scenes it's going to perform the linear regression formula here. So y equals x, a, t plus b. But in our case, we've got weight and bias. So let's go back. It's now time to write some training code. But before we do, let's set the model to use the target device. And so in our case, we've got a device of
I thought I saw something on my secondary monitor.
CUDA.
Yeah.
But because we've written device agnostic code, if we didn't have access to a CUDA device, a GPU, our default device would be a CPU. So let's check the model device. We can do that first up here. Check the model current device, because we're going to use the GPU here, or we're going to write device agnostic code. That's better to say. Device agnostic code. That's the proper terminology. Device, what device are we currently using? This is the CPU, right? So by default, the model will end up on the CPU, but if we set it to model one call.2 device, what do you think it's going to do now? If our current target device is CUDA, we've seen what 2 does in the fundamentals section. 2 is going to send the model to the GPU memory. So now let's check where the parameters of our model live, .device. If we send them to the device, previously it was the CPU. It's going to take a little bit longer while the GPU gets fired up and goes, Pytorch goes, hey, I'm about to send you this model. You ready for it? Boom, there we go, wonderful. So now our model is...
But then... Have we set the target device?
Have access to a CUDA case of CUDA, but because we've written device agnostic code, if we didn't... And so in our case, let's set the model to use the target device. And so in our case, we've got a device of CUDA, but because we've written device agnostic code, if we didn't have access to a CUDA device, a GPU, our default
device is gonna be CPU if torch.is available, right? Device available, is available. What is the target method? Device available. What is the torch.cuda.is available? As CPU, and let's just see what devices. Yesterday, was it yesterday? Yeah, yesterday I did have a rate limit. Let's see whether that's gone now. Can I, if I change my runtime? Well, I need to run this anyway, so I guess let's just do it. Let's change it to a GPU. Hopefully this works, fingers crossed. Let's see, let's check. Yay, we got a GPU. In that case, as expected, we need to re-import everything again. So import torch, from torch import nn, then from matplot. You know what, that should be fine. We'll import the other 2 functions when we need it. Alright, we are on CUDA now. So
default device would be a CPU. So let's check the model device. We can do that first up here. Check the model current device, because we're going to use the GPU here, or we're going to write device agnostic code. That's better to say. Device agnostic code, that's the proper terminology. Device, what device are we currently using? This is the CPU, right? So by default, the model will end up on the CPU, but if we set it to model 1 call.2 device, what do you think it's going to do now? If our current target device is CUDA, we've seen what 2 does in the fundamentals.
Have we defined model 1 though? Oh, we have in this block. Alright, so in that case, let's do check the model current device. Oh, let's just set it up anyways. Model 1.2, because it should be anyway be in the GPU, right?
Section 2 is going to send the model to the GPU memory. So now let's check where the parameters of our model live. Device. If we send them to the device, previously it was the CPU. It's going to take a little bit longer while the GPU gets fired up and Pytorch goes, hey, I'm about to send you this model. You ready for it? Boom, there we go, wonderful. So now our model is on the device, or the target device, which is CUDA. And if CUDA wasn't available, the target device would be CPU, so this would just come out just exactly how we've got it here. But with that being said, now let's get onto some training code. And this is the fun part. What do we have to do? We've already seen this. For training, I'm just going to clear up our workspace a little bit here. For training, we need, this is part of the Pytorch workflow, we need a loss function. What does a loss function do? It measures how wrong our model is. We need an optimizer. We need a training loop and a testing loop. And the optimizer, what does that do? Well, it optimizes the parameters of our model. So in our case, model 1.stateDict, what do we have? So we have some parameters here. Within the linear layer, we have a weight and we have a bias. The optimizer is going to optimize these random parameters so that they hopefully reduce the loss function, which, remember, the loss function measures how wrong our model is. So in our case, because we're working with a regression problem, let's set up the loss function. And by the way, all of these steps are part of the workflow. We've got data ready, we've built or picked a model, we're using a linear model, now we're up to here, 2.1, pick a loss function and an optimizer. We're going to do build a training loop in the same session.
So the loss function that we picked up was L1 loss, right? Oh, wait, what did I do? Never mind, let's get rid of this cut cell. Now it's in some other, oh, is it in dot and then L1? Yeah, there you go. Oh, size average reduced. Now we're gonna keep it as it is. Then we need our optimizer, which we took as SGD. S stands for some complicated word, which just stands for random gradient descent. If you want the correct terminology though, okay, how do you pronounce that? Stochastic. Stochastic, alright. Stochastic basically stands for random. They could have used random, they just wanna overcomplicate things.
Because you know what? We're getting pretty darn good at this. Loss function equals what? Well, we're going to use L1 loss. So let's set that up. nm.L1 loss, which is the same as MAE. And if we wanted to set up our optimizer, what optimizer could we use? Well, Pytorch offers a lot of optimizers in torch.optim, SGD. That's stochastic gradient descent, because remember, gradient descent is the algorithm that optimizes our model parameters.
We have a second viewer right now. Hi to whoever's watching, welcome to my stream. Just learning some Pytorch over here. You can ask any questions if you have any on the chat.
Atom is another popular option. For now, we're going to stick with SGD. LR, which stands for learning rate. In other words, how big of a step will our optimizer change our parameters with every iteration? A smaller learning rate, so such as 0.001, will be a small step, and then a large learning rate, such as 0.1, will be...
Oh yeah, we need to define the learning rate, right? What's going to be our learning rate? Let's just put it as
a larger step. Too big of a step, our model learns too much and it explodes. Too small of a step, our model never learns anything. But, oh, we actually have to pass params first. I forgot about that. I got ahead of myself with the learning rate. Params is the parameters we'd like our optimizer to optimize. So in our case, it's model1.parameters because model 1 is our current target model. Beautiful. So we've got a loss function and an optimizer. Now, let's write a training loop. So I'm going to set torch manual seed so we can try and get as reproducible as results as possible. Remember, if you get different numbers to what I'm getting, don't worry too much if they're not exactly the same. The direction is more important. So that means if my loss function is getting smaller, yours should be getting smaller too. Don't worry too much if your fourth decimal place isn't the same as what my values are. So we have a training loop. ready to be written here.
Alright.
Epochs. How many should we do? Well, we did 200 last time. That worked pretty well, so let's do 200 again. Did you go through the extra curriculum yet? Did you watch the video for the unofficial Pytorch optimization loop song yet? This one here. Listen to the unofficial Pytorch optimization loop song. If not, it's okay. Let's sing it together. So for an epoch
I did see.
in range, epochs, we're going to go through the song.
I'll do it by myself first and we'll come back. That's fine. Epochs is gonna be 200. I'll create my own song, you know. And yeah, epochs 200 for epoch in range. Epochs, Mr. H there, made a typo. I misspelled that. For epoch in range epochs, first we have to make our predictions. Well, first we have to train our model, so let's do that. So model 1.train, then we have to make our predictions, which I'm just gonna call ypred. That's gonna be model 1, and we are gonna pass it our what's it we're gonna pass it the x train because we're training it, right? Then what we're gonna do is we're gonna calculate our loss, which is gonna be our loss function. We're gonna give it our what the predictions that it met and compare it with our y train. Next what we're gonna do is, so we had made our prediction, that is we applied our forward method, and then we have calculated our loss. Should I print it? Let's just keep it as it is. Now what I'm gonna do is, now that I have the loss, I'm gonna do see, you know what, I'm just gonna move my overlay just for a bit. Still, you know, I'm just gonna hide yeah, I'll be right back. Just give me like 1 minute. I'll be right back. Oops, I forgot I haven't unmuted myself. Anyway, let's just start. We have some apples to munch on too. Anyhow, so where were we? Yeah, we calculated the loss. Now we need to do our backward. It's probably loss function dot backward, right? Oh, is it just loss dot backwards? I keep forgetting. It's loss dot backward. Okay. We calculate our loss, then we go backwards, and then we call in our optimizer, right? Optimize our function. What exactly did we do here though? I keep forgetting. We take a dot step, that's what. We move to the next step after calculating the gradient that's required. Do we pass in the laws here? Let's read the docs. No, we don't. What does this return though? Anyway, we do that, and then there's one more step which comes after we calculate the loss. That is, we need to set the optimizer to 0 grad so that the gradients doesn't accumulate onto themselves, and hence our performance increases, efficiency increases. I think, yeah, that should give us the, let's plot the like how we did before. Let's just plot the epoch values. If epoch on every 10th epoch value, let's do our test loop. Oh, actually we need to do model.divide, right? And then we are going to our testing phase now. Testing phase. For the testing phase, we're just gonna do actually, when should we do our testing phase? We don't need to do it every time, right? Oh, we need to do it every time. Yeah, of course we need to do it every time. So the testing phase is just gonna be, we're just gonna call our model on what? Model on our X test, and then is gonna calculate the test loss.
Second, we're going to set model to train. In our case, it's model 1, model to train. Now, step number 1 is what? Do the forward pass. This is where we calculate the predictions. So we calculate the predictions by passing the training data through our model. And in our case, because the forward method in model 1 implements the linear layer, this data is going to go through the linear layer, which is torch.nn.linear, and go through the linear regression formula. And then we calculate the loss, which is how wrong our model's predictions are. So the loss value equals loss fn. And here we're going to pass in ypred and ytrain. Then what do? We zero the optimizer, optimizer 0 grad, which, because by default the optimizer is going to accumulate gradients behind the scenes, so every epoch we want to reduce those back to 0 so it starts from fresh. We're going to perform back propagation here, back propagation, by calling loss.backwards. If the forward pass goes forward through the network, the backward pass goes backwards through the network, calculating the gradients for the loss function with respect to each parameter in the model. So optimizer step, this next part, is going to look at those gradients and go, you know what, which way should I optimize the parameters? So because the optimizer is optimizing the model parameters, it's going to look at the loss and go, you know what, I'm going to adjust the weight to be increased, and I'm going to lower the bias and see if that reduces the loss. And then we can do testing. We can do both of these in the same hit. Now, we are moving quite fast through this because we spent a whole bunch of time discussing what's going on here. So for testing, what do? We set the model into evaluation mode. That's going to turn off things like dropout and batch normalization layers. We don't have any of that in our model for now, but just it's good practice to always call eval whenever you're doing testing. And same with inference mode. We don't need to track gradients and a whole bunch of other things Pytorch does behind the scenes when we're testing or making predictions. So we use the inference mode context manager. This is where we're going to create test pred, which is going to be our test predictions, because here we're going to pass the test data features, forward pass through our model, and then we can calculate the test loss, which is our loss function, and we're going to compare the test pred to y test. Wonderful. And then we can print out what's happening. So what should we print out? How about if epoch divided by 10 equals 0, so every 10 epochs, let's print something out. Print, we'll do an F string here. Epoch is epoch, and then we'll go loss, which is the training loss, can just be equal to the loss, and then we'll go test loss is equal to test loss. So do you think this will work? It's okay if you're not sure, but
then equals 0, then we print what's happening. So epoch, we print the epoch count that we're on, and let's print the loss, and let's also print the test loss. Cool. There we go.
Let's find out together, hey? Oh, we need a bracket there. Oh my goodness, what's going on? Runtime error. Expected all tensors to be on the same device. Oh, of course. Do you know?
Now let me just see what. Not have extreme. Oh, because I need to go ahead and set that right. I need to see. Yeah, because we changed the runtime. Let me just redefine all of these. 1 second. Split data. No, that doesn't work. MX is not defined. Let's do this. Do this. And we need our plot predictions. So, plot predictions. Let's go to the first. Yep, there we go. Let's go to the last. Yep. And that should give me, well, it should still result in an error, but an error which should be expressed alternates. Okay, cool. So let's see why it set that expected on which time.
You know what's happening here? But we found at least 2 devices, CUDA and CPU. Yes, of course, that's what's happened. So what have we done? Up here, we put our model on the GPU. But what's going on here? Our data, is our data on the GPU? No.
Nah, it isn't on the GPU. Oh my god, alright. In that case, all we have to do from our side would be to just, let's just do it in another X-train. We actually need to do it for all the things now, don't we? No, let's just go back to the area where we define our data, or rather create our data, which is gonna be before this. Yeah, there we go. So a range n step is, does this have device? Let's just move this to device is equal to device, and that should work. And now if we run this should work.
No, it's not. By default, it's on the CPU. So we haven't written device agnostic code for our data. So let's write it here. Put data on the target device. Device agnostic code for data. So remember, one of the biggest issues with Pytorch, aside from shape errors, is that you should have your data or all of the things that you're computing with on the same device. So that's why if we set up device agnostic code for our model, we have to do the same for our data. So now let's put xtrain to device, ytrain equals ytrain to device. This is going to create device agnostic code. In our case, it's going to use CUDA because we have access to a CUDA device. But if we don't, this code will still work. It will still default to CPU. So this is good. I like that we got that error because that's just some of the things you're going to come across in practice, right? So now let's run this. What's happening here? Hey, look at that. Wonderful. So our loss starts up here, nice and high, and then it starts to go right down here for the training data. And then the same for the testing.
Wait. Let me join in the fun. There we go. Optimizers and define. Okay, let's define our functions. Torch.lm has no attribute sgd. So where is sgd? Oh, it's in torch.optim. Alright, optim would probably stand for optimizer. That should work, and now this should work. No? Okay. Another typo there. Typos aside.
Data. Beautiful. Right up here, and then all the way down. Okay, so this looks pretty good on the test data set. So how can we check this? How can we evaluate our model? Well, one way is to check its state, Dick.
Oh, I think I might have
So
run it 10 times anyhow. Let's do one thing. Let's just create the model once more. So where is it? Yeah, there we go. Let's run this.
state dict. What do we got here? What are our...
Expect all tensors to be on the same device. What went wrong here? I just ran this part of it, right? Oh yeah, I need to run this. And now I need to run this.
weight and bias. Oh my gosh, so close. So we just set weight and bias.
Why do I this isn't anywhere close to the numbers that I had defined, unless I defined the wrong weight and bias. Let's just see what our weight and bias are. No, they are. Let's just run this again. Interesting. Let's copy this, put this here, run this. Then let's we have model 1. We use model 0 here by any chance? No, I didn't. Everything's model 1. Then let's just call our optimizer functions again.
Bias before to be...
For some reason I need to call the optimizer function again before maybe this, it's because of the optimizer function probably.
0.7 and 0.3. So this is what our model has estimated our parameters to be based on the training data. 0.6968. That's pretty close to 0.7, nearly perfect. And the same thing with the bias, 0.3025 versus the perfect value is 0.03. But remember, in practice, you won't necessarily know what the ideal parameters are. This is just to exemplify what our model is doing behind the scenes. It's moving towards some ideal representative parameters of whatever data we're working with. So in the next video, I'd like you to give it a go or before we get to the next video, make some predictions with our model and plot them on the original data. How close do the green dots match up with the red dots? And you can use this plot predictions formula or function that we've been using in the past. So give that a go, and I'll see you in the...
I need to plot what?
With our model and plot them on the original data. How close do the green dots match up?
Let's see, let's plot predictions and ypred. No, not ypred. Predictions is gonna be by let's just do test predictions, because we'll move this over here and we'll call it test spreads. Let's have this underneath, not this one. Test spreads, okay. Not test spreads, test spread, and let's call this, let's change the name here so that it doesn't raise an error. For predictions is equal to test spread, and what else do I need? Okay, with the predictions, oh yeah, we'll just run it from the beginning so that we get the initial prediction, and then we just see it visually basically. Alright, so let's do that. For us to do that, we need to run. What exactly do we need to run? We need to run this. Let's actually move this up here. Oops, no. Let's remove this cell. Let's run that, and you know what, let's also move this that should be good. Let that run. And now we are gonna run this, which would result in an error. Name PLT is not defined. Okay, that's because when I defined plot predictions, we need to, there should be a, there we go. Let's go to the last call. No, let's go to the last cell. And now run this. And we got an error. Can't convert CUDA 0 device 10 tensor to numpy. Predictions. We need to convert it into a numpy array, huh? Alright, let's do that. Let's do that. So
with the red dots. And you can use this plot predictions formula or function that we've been using in the past. So give that a go, and I'll see you in the next video. But congratulations, look how quickly we just...
let's see. Can't convert CUDA. Alright, but where exactly, like which line? Yeah, show me in depth. Scatter training data and test data. Okay, you know what? Let's just convert that to numpy. So what we need to do is tensor to numpy array. Yep. Just want to check whether my caps lock was turned off or not. Let's see. Torch tensor. Alright, let's do this. We just need to do dot numpy, right? Numpy. Well, what does dot numpy do? Yeah, it just turns that to a numpy array. Dot numpy. And we also do dot numpy here. That should hopefully work for us. Now how yeah, let's quit that, run that, I mean rerun that. In fact, let's just run this and hopefully now I get it when Daniel wasn't kidding when he said this is a common error you come across in Pytorch. Tensor.cpu train data.cpu. Let's actually do .cpu commands. Let's run our this code block. I did do that, didn't I? For the frames, it's the same line which is giving us the, it's line 17, which is train data. Okay, let's just use Stack Overflow. Isn't that what I did? Troubleshooting on the fly is what you're seeing here. As Daniel would like to put it. Anyhow, now let's see. .th detach computation CPU allocate tensor and RAM. Clone the tensor node to modify the output in place. Port tensor to numpy. I mean, isn't this what I did though? Okay, our tensor is in the GPU right now, and we need to convert it into. Let's just. I think we can figure this out on our own. Let's. Okay, you know what? Show me the. Is this the place? Yep. Let's just copy this set. Put it over here first. Dot CPU 2. Just move it over to the CPU and do dot numpy. That should work, shouldn't it? Let's see where exactly that I came from. That in, okay. CPU. Can numpy arrays be stored in GPU? No. Numpy doesn't use. Okay, alright, okay, gotcha. In that case, let's copy it over and then use it. So does this work in that case? And well, I didn't that, I meant this. Alright, okay. Convert tensor to on GPU to numpy array. Alright, there we go. You only need to call to you. Okay, so this should work. You know what, let me just set train data to be this. And here I'll just give it the train data. And let's see. And hopefully no, it's this. Okay. What exactly is going on? If I can't use a CPU and GPU at the same time. You know what, I just
Train a model using the steps that we've covered in a bunch of videos so far and device agnostic code. Oh, so good. I'll see you soon. In the last video, we did something very, very exciting. We worked through training an entire neural network. Some of these steps took us an hour or so worth of videos to go back through before, but we coded that in one video. So you ready to sing the song just to remind ourselves of what's going on? For an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Let's test. Call model.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. And then we do it again. For another epoch in a range. No, I'm kidding. We'll just leave it there. But that's the unofficial Pytorch optimization loop song. We created some device agnostic code so that we could make the calculations on the same device as what our model is, because the model's also using device agnostic code. And so now we've got to evaluate our model. So we've looked at the loss and the test loss here, and we know that our model's loss is going down, but what does this actually equate to when it makes predictions? That's what we're most interested in, right? And we've looked at the parameters. They're pretty close to the ideal parameters. So at the end of last video, I issued you the challenge to making and evaluating predictions, to make some predictions and plot them. I hope you gave it a shot. Let's see what it looks like together, hey? So turn the model into evaluation mode. Why? Because every time we're making predictions or inference, we want our model to be in eval mode, and every time we're training, we want our model to be in training mode. And then we're going to make predictions on the test data, because we train on the trained data and we evaluate our model on the test data that our model has never actually seen, except for when it makes predictions. With torch inference mode, we turn on inference mode whenever we make inference or predictions. So we're going to set ypreds equal to model1, and the test data goes in here. Let's have a look at what the ypreds look like. Wonderful. So we've got a tensor here. It shows us that they're still on the device CUDA. Why is that? Well, that's because previously we set the model 1 to the device, the target device, the same with the test data. So subsequently, our predictions are also on the CUDA device. Now, let's bring in the plot predictions function here. So check out our model predictions visually. We're going to adhere to the Data Explorer's motto of visual set to... Oh, we got another error. Type error. Can't convert CUDA device type tensor to numpy. Oh, of course. Look what we've done. So our plot predictions function, if we go back up, where did we define that? What does our plot predictions function use? It uses matplotlib, of course, and matplotlib works with numpy, not Pytorch, and numpy is CPU-based. So, of course, we're running into another error down here, because we just said that our predictions are on the CUDA device. They're not on the CPU, they're on a GPU. So it's giving us this helpful information here. Use tensor.cpu to copy the tensor to host memory first. So this is our tensor. Let's call .cpu and see what happens then. Is that going to go to CPU? Beaut. Oh my goodness. Look at that. Look at that. Go the linear layer.
Wait, what?
The red dots, the predictions, are basically on top of the testing data. That is very exciting.
Yeah, that still doesn't work.
Here, use tensor.cpu to copy the tensor to host memory first. So this is our tensor. Let's call .cpu and see what happens then. Is that going to go to CPU? Beaut. Oh my goodness. Look at that. Look at that. Go the linear layer. The red dots, the predictions, are basically on top of the testing data. That is very exciting. Now again, you may not get the exact same numbers here, and that is perfectly fine, but the direction should be quite similar. So your red dot
let's just remove this. Let's just bring back everything as it was. Maybe it's still using for him it might be using the extreme from the earlier function when it was still in the CPU. $9.15. It's without train data, isn't it? Data dot CPU dot parameters. We're gonna convert this to a list, and then we're gonna call the device. Let's see what that prints for us. This 10 subject has no check what device pencil is Pytorch. Get device. Okay. Alright, let's just do get device. Can't convert coda. Maybe others have come across the same issue. Okay, we're gonna change this no matter what. Maybe it's maybe it's something very Wait, is it? Oh my god. It was because of this, isn't it? Finally. Anyhow, let's see. Plot predictions. Test spread dot. What's the error now? Let's just do .cpu here and that thing. That took us forever. Not gonna lie, that was a bit stressful. When I run this. There we go. I can't tell you how happy I am right now. Although what just happened here? Not exactly what I expected. How many times are you running this? 200 times, right? Maybe the map is just too much or something. Yeah, let's just call it
Results should be based. Basically on top of the green dots, if not very slightly off, but that's okay. That's okay. We just want to focus on the direction here. So thanks to the power of backpropagation here and gradient descent, our model's random parameters have updated themselves to be as close as possible to the ideal parameters, and now the predictions are looking pretty darn good for what we're trying to predict. But we're not finished there. We've just finished training this model. What would happen if our notebook disconnected right now? Well, that wouldn't be ideal, would it? So in the next part, we're going to move on to 6.5, saving and loading a trained model. So I'm going to give you a challenge here as well, is to go ahead and go back and refer to this code here, saving model in Pytorch, loading a Pytorch model, and see if you can save model 1, the state dictionary of model 1, and load it back in and get something similar to this. Give that a shot, and I'll see you in the next video. Welcome back. In the last video, we saw the completeness, and this is just so if you didn't have a models directory, this would create one. So model path.
You know what? Let's just do it anyways. Gosh, I'm so tired right now.
Try and save and load the model yourself. I hope you gave that a go, but we're going to do that together in this video. So we're going to start by importing path because we would like a file path to save our model to. And the first step we're going to
It's not. I don't think it's made to be used 24 hours.
do is create models directory. We don't have to recreate this because I believe we already have one, but I'm going to put the code here just for completeness. And this is just so if you didn't have a models directory, this would create one. So model path is going to go to path models, and then we'd like to model path.makedir. We're going to call makedir for make directory. We'll set parents equal to true, and if it exists, okay, that'll also be true, so we won't get an error. Oh my gosh, Google Colab, I didn't want that. We won't get an error if it already exists. And 2, we're going to create a model save path. So if you recall that Pytorch objects in
What name did
general
you
have the
first
extension of
say?
what? That we're going through. This one here.
PTH, right?
Yeah, chapter 01. PyTorch workflow, model 1, and they usually have the extension .pt for PyTorch or PTH for PyTorch as well. I like PTH. But just remember, sometimes you might come across slightly different versions of that, PT or PTH. And we're going to create the model save name, or the save path. It's probably a better way to do it. Is going to be model path, and then we can use, because we're using the path lib module from Python, we can save it under model name. And so if we look at this, what do we get? Model save path. We should get, oh, path is not defined. Oh, too many capitals here. Path. We should get, oh, path is not defined. Oh, too many capitals here, Daniel. The reason why I'm doing these in capitals is because oftentimes hyperparameters, such as epochs in machine learning, are set as hyperparameters. LR could be learning rate. And then you could have, as well, model name equals, yeah. But that's just a little bit of nomenclature trivia for later on. And model save path, we've done that. Now we're going to save the model state dictionary rather than the whole.
Alright, and to do that, how did we save it again? We do model 1 dot save, right? That's just to save it normally, but we don't want to save it normally, so we pull up the docs. Save model. Torch dot save. Yeah,
Whole model, save the model state dict, which you will find the pros and cons of in where? In the PyTorch documentation for saving and loading a model, which was a little bit of extra curriculum for a previous video. But let's have a look at our model save path. We'll print it out and we'll go torch save. We'll set the object that we're trying to save to equal model1.stateDict, which is going to contain our trained model parameters. We can inspect what's going on in here, state dict. That'll show us our model parameters. Remember, because we're only using a
save model 1 dot detect into our model save path.
single linear layer. We only have 2 parameters, but in practice, when you use a model with maybe hundreds of layers or tens of millions of parameters, viewing the state dict explicitly like we are now might not be too viable of an option, but the principle still remains. A state dict contains all of the model's trained or associated parameters and what state they're in. And the file path we're going to use is, of course, the model save path, which we've seen here is a POSIX path. Let's save our model. Wonderful, saving model to this file path here. And if we have a look at our folder, we should have 2 saved models now. Beautiful. 2 saved models. This one was from the workflow we did before up here, saving a model in PyTorch, loading a PyTorch model, and now the one we've got, of course, model 1 is the one that we've just saved. Beautiful. So now let's load a model. We're going to do both of these in one video. Load a PyTorch model. You know what? Because we've had a little bit of practice so far and we're going to pick up the pace. So let's go loaded, let's call it, we'll create a new instance of loaded model 1, which is, of course, our linear regression model v2, which is the version 2 of our linear regression model class, which subclass is what? Subclass is nn.module. So if we go back here, up here to where we created it, so linear regression model v2 uses a linear layer rather than the previous iteration of linear regression model, which we created right up here. If we go up to here, which explicitly defined the parameters and then implemented a linear regression formula in the forward method. The difference between what we've got now is we use PyTorch's pre-built linear layer, and then we call that linear layer in the forward method, which is probably the far more popular way of building PyTorch models, is stacking together pre-built NN layers and then calling them in some way in the forward method. So let's load it in. So we'll create a new instance of linear regression model v2. And now what do we do? We've created a new instance. I'm just going to get out of this, make some space for us. We want to load the model state dict, the saved model 1 state dict, which is the state dict that we just saved beforehand.
We need to call v2, don't we?
So we can do this by going loaded model 1, saved that PyTorch object before.
It's called load state dict.
But the reason why we use the path lib is so that we can just call model save path in here. Wonderful. And then let's check out what's going on. Or actually, we need to put the target model or the loaded model to the device. The reason being is because we're doing all of our computing with device agnostic code. So let's send it to the device. And I think that'll be about it. Let's see if this works. Oh, there we go. Linear regression model v2. In features 1, out features 1, bias equals true. Wonderful. Let's check those parameters, hey? Next, loaded model 1.parameters. Are they on the right device? Let's have a look. Beautiful. And let's just check the loaded state dictionary of loaded model 1. Do we have the same values as we had previously? Yes, we do. Okay, so to conclusively make sure what's going on, let's evaluate the loaded model. Evaluate loaded model. Loaded model 1, what do we do for making predictions, or what do we do to evaluate? We call .eval. And then, if we're going to make some predictions, we use Torch inference mode with Torch inference mode, and then let's create loaded model 1 preds. Equals loaded model 1, and we'll pass it the test data. And now let's check for equality between ypreds, which is our previous model 1 preds that we made up here, ypreds, and we're going to compare them to the fresh loaded model 1 preds. And should they be the same? Yes, they are. Beautiful. And we can see that they're both on the device. How amazing is that? So I want to give you a big congratulations because you've come such a long way. We've gone through the entire Pytorch workflow, from making data, preparing and loading it, to building a model. All of the steps that come in building a model, there's a whole bunch there. Making predictions, training a model. We spent a lot of time going through the training steps, but trust me, it's worth it because we're going to be using these exact steps all throughout the course. And in fact, you're going to be using these exact steps when you build Pytorch models after this course. And then we looked at how to save a model so we don't lose all our work. We looked at loading a model, and then we put it all together using the exact same problem, but in far less time. And as you'll see later on, we can actually make this even quicker by functionizing some of the code we've already written. But I'm going to save that for later. I'll see you in the next video where I'm just going to show you where you can find some exercises and all of the extra curriculum I've been talking about throughout this section 01 Pytorch workflow.
Wait, what's that? What's that? Hey, we have one of the person in the chat. AnkQVPSN. 10 viewers for free, what? Viewers pro, what is this? I thought it was, I think it's a bot or something.
I'll see you there. Welcome back. In the last video, we finished up putting things together by saving and loading our trained model, which is super exciting because that's come to the end of the Pytorch workflow section. So now this section is going to be exercises and extra curriculum, or better yet, where you can find them. So I'm going to turn this into Markdown, and I'm going to write here for exercises and extra curriculum, refer to. So within the book version of the course materials, which is at learnpytorch.io, we're in the 01 section, Pytorch Workflow Fundamentals. There'll be more here by the time you watch this video, likely. And then if we go down here, at the end of each of these sections, we've got the table of contents over here. We've got exercises and extra curriculum. I listed a bunch of things throughout this series of 01 videos, like what's gradient descent and what's backpropagation. So I've got plenty of resources to learn more on that. There's the loading and saving Pytorch documentation. There's a Pytorch cheat sheet. There's a great article by Jeremy Howard for a deeper understanding of what's going on in torch.nn. And there's, of course, the unofficial Pytorch optimization loop song by yours truly, which is a bit of fun. And here's some exercises. So the exercises here are all based on the code that we wrote throughout section 01. So there's nothing in the exercises that we haven't exactly covered. And if so, I'll be sure to put a note in the exercise itself. But we've got create a straight line dataset using the linear regression formula. And then build a model by subclassing nn.module. So for these exercises, there's an exercise notebook template, which is of course linked here. And in the Pytorch Deep Learning GitHub, if we go into here, and then if we go into extras, and if we go into exercises, you'll find all of these templates here. They're numbered by the same section that we're in. This is Pytorch workflow exercises. So if you wanted to complete these exercises, you could click this notebook here, open in Google Colab. I'll just wait for this to load. There we go. And you can start to write some code here. You could save a copy of this in your own Google Drive and go through this. It's got some notes here on what you should be doing. You can, of course, refer to the text-based version of them. They're all here. And then if you want an example of what some solutions look like, now, please, I can't stress enough that I would highly, highly recommend trying the exercises yourself. You can use the book that we've got here. This is just all the code from the videos. You can use this. You can use, I've got so many notebooks here now. You can use all of the code that we've written here to try and complete the exercises, but please give them a go yourself. And then if you go back into the extras folder, you'll also find solutions. And this is just one example, solutions for section 01. But I'm going to get out of that so you can't cheat and look at the solutions first. But there's a whole bunch of extra resources all contained within the Pytorch Deep Learning repo. Extras, exercises, solutions, and they're also in the book version of the course. So I'm just going to link this in here. I'm going to put this right at the bottom here. Wonderful. But that is it. That is the end of the section 01 Pytorch workflow. So exciting. We went through basically all of the steps in a Pytorch workflow, getting data ready, turning it into tensors, build or pick a model, picking a loss function, an optimizer, we built a training loop, we fit the model to the data, we made a prediction, we evaluated our model, we improved through experimentation by training for more epochs, we'll do more of this later on, and we saved and reload our trained model. But that's going to finish 01. I will see you in the next section. Friends, welcome back. We've got another very exciting module. You ready?
Alright, I think I'll call it a day for now. We are almost on to the 4-hour mark. 3 hours, 54 minutes in according to Twitch. It's been a very long one, but we have finally made our first, machine learning model, and I'm so happy for that. The progress that we made today is amazing. So, I'm gonna end the stream now. It was a very nice day, and I'm tired, very, very tired. But it was worth it. I really enjoyed the sessions today. So yeah, I'll see you tomorrow, I guess. Take care.